Good evening and welcome to Lockdown Livestream Extended Edition. Before we commence, I'd like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respects to the elders past, present and extend that respect to all Aboriginal and Torres Strait Islander people today. Tonight, the Astronomical Society of Victoria, in conjunction with the Astronomical Society of South Australia and Perth Observatory, is proud to bring you our Lockdown Livestream Extended Edition. With the vast majority of the country currently in lockdown, we felt that we should do what we can to break up the monotony of lockdown and to give you viewers a look into the universe above us. We aim tonight to share with you a tour of the Milky Way, using a program called Space Engine and images of objects taken by our live stream team. The team will answer your questions on all things astronomy. So if you have any questions, please pop them in the chat section and we will answer them as best we can. But to kick the night off, I'd like to welcome Astrophysicist Clare Kenyon and ASV astronomy guru Trifid Nebula to have a quick chat before we bring in the rest of the team. So grab a drink, get cozy and sit back and enjoy the ride as we fly our way through the Milky Way and beyond. Good evening, Stefan.
Hey, nice to be here.
And good evening, Claire.
Hi, everyone. Thanks for having me.
So before we get into things, I just wanted to have a chat with the two of you as, I guess, the ASV's most knowledgeable people from my point of view, and have a chat about, I'll put the first question really to Claire, because this sort of goes to what we're trying to do tonight and discuss and sort of teach people about STEM. And I know that's a big passion of yours. So I guess the question is, why is STEM so important to astronomy?
Well, STEM's important to everyone all the time. I think astronomy particularly is just us looking up and going, well, what is that and what's it there for and how do I know anything about it? And I think that probably links back to bigger questions that we have in what is STEM and why is it important in general. And the main reason I would say is we need STEM because it gives us the ability to think critically, the ability to ask a question, find an answer, and judge whether or not, this is the most important part, judge whether or not that answer is actually a good fit for the question so that we can then go on to solve other problems. In general, STEM also pushes us further forward towards better societies and living standards overall. It helps actually address inequalities in societies as well. Some of the work I do is actually in Kathmandu. I run a Kathmandu astrophysics school over there, and it's already gone through the third iteration, and there's actually very clear links between having increased capability in STEM, in this case through astrophysics and astronomy, and actually linking it in with female participation, increasing that in STEM, and also then that barrels on to increasing STEM capability within the actual country. And then that actually peters down into industry and their GDP. There's actually long-term studies that show that STEM is actually vital to the health and well-being of a nation's industry.
Wonderful answer. Now, Stefan, one for you. I'd like to know your thoughts on what the best planets to look at in the night sky of the next few months is going to be.
Yeah, well, I think that's a well-timed question. Yeah, definitely. So within the next month, at least, this is the prime time to be getting outside and getting out your telescope, binoculars, whatever you have, and trying to find Saturn and Jupiter, because both of them have orbited around in their orbit to a point where they're actually really close to the Earth, at a point that we call opposition, opposing us and the sun. So they appear quite large in the sky and they're quite well illuminated by the sun. So yeah, absolutely. I believe the exact date of opposition of Saturn is coming up in a few days, and then Jupiter should be around the start of August. So yeah, anytime in the next few weeks, you'll be able to see them. Actually, if you can get out and see the clear sky now, take a look near the moon, and you'll find these two bright points in the sky. The brightest one is Jupiter, the less bright one is Saturn. And then, over the coming months, some of the other planets will start becoming visible. And not for, I think, until about December 2022 is when we'll get the next best view of Mars. But yeah, definitely keep an eye out for Jupiter and Saturn.
And I'm correct, Stefan, in saying that it's going to be very easy tomorrow night to find Saturn, because it will be, in fact, very close to the moon, what we call a conjunction. Well, we might not see the actual conjunction, but very, very close. So tomorrow night's a great night to actually find out which one Saturn is. Jupiter's usually obvious because it's kind of bright and orange and big and out there, but Saturn can be a little bit more tricky for us to be sure that we can see it, unless you've got a really good app. But yeah, look for the moon tomorrow night. So that's a really good way to do that, yeah.
We just need some clear skies. That would be good. Nothing but cloud and rain at the moment. Now, before we bring the rest of the team in, there are a couple of objects in particular that are very interesting objects that Kim from the ASSA, the Astronomical Society of South Australia, is going to discuss tonight. He's going to talk about imaging these through live stacking, but he's also going to talk about the history of one of these objects, which is a very interesting history. So I thought I'd get a sort of an astronomer's view of your thoughts on one of my favourite named objects, the dark Doodad Nebula, and the Gum Nebula. So Claire, if you'd like to have a little bit of a chat to the viewers about those two objects, and just a little bit on those, not too much. We won't steal Kim's thunder.
Well, maybe I'll just make it a really generalized discussion on what nebulae are in general. So nebulae, really, if it comes from the Latin word of the same name, so nebula, it's actually basically a cloud. So vapor, mist, gas, and it's essentially made of that. It's gas and dust. And there are a bunch of different types of nebulae, which is the plural, has an E on the end of the singular nebula. There are a bunch of different types, so there's sort of four main ones. There's the sort of gas and dust that's left over after a supernova goes boom, and that's usually lit up, so it emits light, called an emission nebula, because the actual energy from the supernova is still causing all the atoms inside this gas and dust to get really excited and emit light. So that's called a supernova remnant, and that's a type of nebula. There's a H2 region, which is a star-forming region. And what they are, they're actually lit up from within by stars inside. So the stars glow blue hot, and they've got all this material around them, and they sort of glow. So they're called H2 regions, and they can be really diffuse across the sky. And then you have these planetary nebula, which actually have nothing to do with planets. They're to do with stars of sort of 8 to 10 solar mass, or even low solar masses, and the sun will do this eventually, swells up into a red giant, and then it actually just goes and puffs all of its outer layers off, and then the star inside becomes a white dwarf eventually, and all of this light just lights up that gas. But what's really cool about the Doodad Nebula is it's this other type of nebula, the fourth type, which is called a dark nebula, and it's called that because that's what it is. It essentially soaks up light around it. So it's basically cold gas and dust, and it just sits there. And the Doodad's kind of cool. It's for all you astronomers out there, it takes up almost 3 degrees across the sky, degrees of arc, and it's basically just cold gas and dust in this sort of laneway. And this is actually where it cools down enough that molecules, particularly of H2 gas, with some helium, some carbon monoxide, and other molecules, they can actually form. It's dense enough and cold enough for molecules to form here. And then after that, we start to see the first beginnings of stars, and potentially we see this glowing of stars inside this nebula.
I think you covered that off pretty well. Stefan, do you have anything to add?
Well, I guess I can add from an astrophotographer's perspective. I think as an astrophotographer, our goal is to try and convey the beauty of the universe, and there's no better object to do this than nebulae. Like Claire covered, they come in all different types, shapes and sizes, colors, varieties, and for me, I'm really interested in dark nebulae, in these emission nebulae that Claire talked about. And the dark Doodad is a really fantastic example of this. And the reason that myself as an astrophotographer like these objects is because these are the hardest ones. They don't emit any light like the emission nebulae. They just absorb light from the stars behind them. And so these type of objects, you have to drive far away into the country where there's no light pollution and image for many, many hours on end. But when you see the final photo of these strange dark blobs, you really get this sort of three-dimensional perspective that there is really this giant, immense cloud of dust and gas just sitting there in front of you. Yeah, as I'm sure we'll see with some of the photos tonight, nebulae are just absolute photogenic. We
will indeed. So with that in mind, we'll bring in the rest of the team. We have Matt Woods he's all the way from Perth Observatory, sitting out there in the dark. We have Andy, who's out near the South Australia Victoria border. We've got Paul from the Astronomical Society of South Australia. We have Lee, otherwise known as Prison Break, hiding in Ringwood in Victoria. We have Anne-Marie. Anne-Marie's out bush somewhere north, I know that much. I'm not exactly sure where her location is. One day I'll work it out. And Kim, he's from the Astronomical Society of South Australia as well. And Kim is going to give us a bit of a presentation on live stacking and public outreach in online streaming. There's a fancy name for it that I didn't know about until today. I just thought I'd call it live streaming, but apparently it has a proper name, and Kim will run us through that before we start running through some of the objects that we're going to have a look at tonight. So Kim, the floor is
you're going to do that straight away, huh?
Yes, get stuck into it.
All right, this presentation's a little backwards then. I'll just start with a couple of slides, and then I'll just jump to some of the outreach slides, if that's okay. So let me just bring this up. Hide that. Do that. All right. Can you see that okay?
Yes, we can. Yeah.
Great. Okay, so this is a very small telescope. It's an 80-millimeter refractor. It's got a lens at the front here, and there's nothing else all the way down there except for this other little lens that helps adjust the image. So it's comes out a little flatter and nicer on the camera. The camera is this red can on the back end here. And this whole telescope sits on this white mount, which is computer controlled. And there's a little red computer on the other side of this scope. You can probably just see it poking out between the blue thing and the other, the guide scope on top. And that computer basically controls the entire mount, the telescope, takes images, keeps the images pinpoint, and transmits all that data back to me inside. I don't sit outside anymore. It's pretty horrible, actually, in the wintertime. It's actually worse sometimes in the summertime. But I set up this rig about a year ago, and basically to take images from suburban Adelaide. And I'm fairly close to the centre of the city. My skies are very, very bright, full of light pollution. But there's some amazing stuff you can do, even with a small telescope, using this technology called live stacking, which is basically taking a sequence of images, one after the other, and getting the software in that little computer to actually basically align the images one on top of each other, so the signal becomes more prevalent than the noise. The noise includes light pollution, which you don't want. So gradually the signal starts appearing well and truly above the noise. This whole setup is run off an iPad. There's an image of the iPad on the bottom right there, and typically of what an image might look like on that screen. This screen just shows a few other items on there. You don't have to worry too much about that. This is a view from the other side. The only thing to note here is there's a focusing controller, automatic focuser here. So you don't have to go outside and keep focusing the scope. It's all done electronically and automatically. And you can see the computer there. It's an ASI Air Pro, which has become quite popular in recent times. So the way this works is it takes one image to begin with, and this is a relatively bright image, bright object in the night sky. This is the Eta Carinae Nebula, and this is one 3-minute exposure taken from my backyard. But I've also used what's called an L-extreme filter, which is allows only is a narrowband filter, allows only light from hydrogen alpha gas emissions and also oxygen 3 to pass through to the imaging sensor. You have to look very carefully, but this image is actually not that great. It's actually quite noisy. And if you zoom in a little bit, you can see some of the noise in this region here. You can see some stars, but there's a bit of noise around it. And this is just one exposure. If you take more exposures, the noise gradually starts to go away. What happens is you're averaging out all these images, and the noise is getting washed out, and the signal that you want, which is stars and nebulae, start to come out. So this is 23 exposures, automatically stacked. You don't have to do anything. It just appears magically on your iPad, usually in the lounge room while you're doing something else. And this is a close-up of the final image, just showing the top of the image. And you can start to see there's quite a nice bit of detail coming out here. And really wonderful sort of bits of nebula here and there and dark patches. And this is the lower portion of that image as well. So you can see now the image, the quality of the image has improved considerably. So the whole idea by live stacking is I'll just go back and jump out of that for a moment and go back to the start because it's out of order. The whole idea of live stacking is to come up with a nice image from very little signal amongst the noise, and just pull that signal out from the noise just using this technology. So this is a wonderful technology. You can actually take these images, and in fact that image I've got on screen at the moment was actually taken in suburban Adelaide in what's known as Bortle 8 sky, very bright sky because of the light pollution, and the full moon was in the sky as well. I mean, you look through a telescope, you can barely see this, right? And yet the image, the technology allows you to bring all this detail out. So you can do much better from a dark sky site where the noise from light pollution is even less and there's more signal to play with. So I'll show some images throughout the evening that have been taken both in the Adelaide area region and also out from a dark sky site. But this technology for us, particularly during COVID, is something the Astronomical Society of South Australia is investing in to enable safe viewing of the night sky. So instead of eyepiece views, which traditionally are fairly limited anyhow to bright objects. And I've got a couple of slides here to demonstrate that and actually demonstrate the advantages of this technology. And most people probably know this already, at least in the astronomical community. But here's a couple of cartoons. A conventional astronomy outreach event might be a little bit like this, right? Long queue of people, someone gets to the front of the queue and they see this fuzzy grey thing, right? And that's it. Apart from the very bright objects, the moon and the bright planets, oftentimes the experience can be quite underwhelming for some people. However, it's a complete non-experience for others. You can think of kids. They often struggle to reach the eyepiece, and even then, when they look through, they don't know what they're looking through. They're not even aware of what they need to be seeing. And then there's other folk who we just don't even get that far at all. So what can we do? Well, this is, if you think of live stacking or electronically assisted astronomy, as it's often referred to, it actually enables a vastly improved experience for users. And here I'm talking the general public. So you can actually project these images onto a large screen, and you can have a group presentation and a Q&A session. So it becomes a more engaging experience for everyone. This is how it works. You've got one of these telescopes. I've actually got one behind me. This would have been sitting outside tonight, but it's a bit windy and wet, and there's a few thunderstorms and hail in Adelaide, so I'm not taking it outside, but I can actually operate it, even though it's sitting just behind me at the moment. So you have one of these fancy telescopes. It's connected to an iPad through Wi-Fi. An operator uses an iPad to control the scope, and he may, or she may, simultaneously point out the object in the night sky. What we find is when people see these images on the iPad, they instantly want to know where it is in the sky. So it's a good idea to have a green laser. We then beam that one way or the other to a digital projector, which then puts it up on a screen for an audience. And a presenter then explains the images on screen, and they can also switch between different telescope inputs. You can actually have multiple telescopes feeding into this projection system. And a laser is used to point out specific features on the screen. But there are multiple benefits versus conventional outreach. I mean, for example, you see things in color as opposed to gray, fuzzy stuff that you typically see through an eyepiece. Many fainter objects can be seen. It becomes more like a curated experience. You can actually present compelling in-depth presentations and discussions about what's on the screen and highlight specific elements of the object. Everyone knows what they're looking at. There's no second guessing. You can have a group discussion. It's a collective learning opportunity. This actually works in urban environments as well, even light polluted areas. and with light trespass. It's all access. No one is disadvantaged at the end of the day, and it's COVID safe. So we've actually developed in the society, we've actually started putting together one of these scopes, not just relying upon members. We'll be using that at pop-up events and also at our Winter Star Party, which is occurring on the 14th of August, which is almost entirely sold out now. We may have a few people cancel if you're in South Australia and you want to come along. It's a national science event.
Do we call that shameless self-promotion?
Yeah, we do.
That's all right.
But it is actually a free event. It's for the public, and it's National Science Week, so that's all good.
Now, while I've got your attention, we do have a question. Jenny Kong wants to know, what would a setup like that cost, the one that you use?
Yeah, it's not pretty. This is very much what we're talking about here. It's very much an astrophotography rig, but you can start to compromise on various bits and pieces. It'll be somewhere between $5,000 to $10,000, depending upon what you have. I repurposed my telescope, shown here. I bought this back in 2009 as just a visual scope, but I repurposed it for imaging, and it's working brilliantly for that. So you can trade off on a number of items. You don't necessarily need the guide scope or the very expensive guide scope camera. You can start small, around $5,000, which still is quite expensive, I think. It's really the mount at the end of the day. That's where you end up putting most of your money as a computer-controlled mount. That usually absorbs the most of the budget, quite frankly. And that one there's about $3,000 alone. All right, so I won't go through all these bits and pieces. There are lots of bits and pieces. A lot of fun putting these together. The most expensive piece, apart from the mount, then is the camera. And this camera's been quite successful for this type of work. All right, so that's all I really had for now. I can go on and do some live stack examples a little later on, or right now. I'll leave it up to you, Mark. Just let me know when.
So what we might do is, in my excitement, I forgot to run the intro after I'd spoken to Claire and Stefan. So I'm just going to run our intro, and then when we get back from our lovely little intro video that Leah's put together, we will start looking at our viewing list of images. I'm not sure if we're going to be able to do any live stacking tonight, but we'll definitely have some pre-imaged images of nebula and galaxies and star clusters and even planets that we will be discussing. So enjoy our lovely little introduction, and we will see you on the other side of that.
Hello, darkness, my old friend.
Used to give me rest. I wish you could again, but that was on the outside, and things were different then. We built our world together.
Okay, so that was a lovely little intro that I was meant to play before, but didn't. Apologies for that. That was our lovely lockdown live stream from what we're terming prison. We're all trying to prison break at the moment. Actually, before we jump into the objects tonight, Harry wants to know is can we access the slides that were shown later? So Kim, is that something that is available to those viewing tonight, the slides that you put together or the information that's in those slides?
We'll make it available somehow. We will make it available as a PDF, I think, and we can do that.
Beautiful. All right. So what we might do then is jump into our first object. And the first object that we're going to discuss while Matt gets an item live stacked for us. So Matt's in Perth. He's got clear skies, unlike the rest of us. The first object we're going to talk about is M17, the Omega Nebula, or Swan Nebula. So I know that Lee has an image of that, and Anne-Marie has an image, and so does Paul as well. So if you guys would like to bring those images up, we can have a look at them, and we can get Claire and Stefan to start telling us all about those objects if they know anything about them. Claire's looking at me like, what? Here we go. We've got Paul's got his up. There we go. So, Stefan, would you like to talk to us about the Swan Nebula?
Sure. Yeah, I'll kick it off. So, as Claire was describing before, there are many different types of nebulae, and this is a real prime example of what we call an emission nebula. So, this type of nebula, it's a big cloud of gas and dust that's being excited by high energy radiation coming from newly born stars within it. And so these newly born stars are emitting high energy radiation, mostly ultraviolet, and that high energy radiation is being absorbed by some of the atoms within this cloud, which is mostly hydrogen. And when these atoms relax back down, they re-emit radiation, which we can then see. It's in the optical wavelength, and it appears mostly red, which is why you see most of these emission nebulae have this sort of red coloration. And so this particular nebula, M17, or the Swan or Omega, it's got a few different names. It's located in the constellation Sagittarius, and it's around 5,000 to 6,000 light years away. It's magnitude 6, and magnitude, if you haven't heard of that before, is it's a measurement of its brightness. So it's apparent brightness as we see it. And magnitude 6 is fairly bright as far as nebulae go. And this nebula, its core is quite bright. In fact, you can see it even with binoculars in a dark sky. So it's a real treat for astronomers and also astrophotographers. So it's around 5,000 to 6,000 light years away. It's around 40 light years in diameter. And it's actually one of the most massive and brightest star-forming regions within our local area of the galaxy. So if you're an astronomer, an astrophotographer, and you've seen the M42, the Orion Nebula, you'll know that it looks quite different to this, but actually this cloud has a very similar geometry to the Orion Nebula. It's just that we're seeing it from a different perspective. We're seeing it sort of edge on instead of face on, as with the Orion Nebula. And M17, this nebula, it's actually a lot more massive than M42. This contains hundreds of O-type stars, which are very, very massive, very young, very hot stars. And in its core, it's got an open cluster embedded within it that's catalogued as NGC 6618. It's one of the youngest open clusters that we know.
So I might just jump in there and just
yeah, go for it. Jump in.
A little bit about stars, and so what Stefan just mentioned was that we have these O-type stars, and there are also B-type stars in there. And well, what are those? But so why do we say O? What's the letter O and what's the letter B for? There's a sort of a categorization of stars based on basically color. So you might have heard the, I forget what they're called, like mnemonic. O, be a fine girl or guy, just kiss me or kiss me. And then there's some letters after that. And they basically talk about the types of stars from most massive and energetic and bright and blue, all the way down to the small little red nothings, red dwarfs. So when we talk about O's and B's, they're the hottest, biggest superstar stars. Like we're talking, between 10 and 30 Kelvin for B types, and O are hotter than that. So these stars really are blue when you look at them. They're the blue supergiants. They're the ones that basically go through their lives really, really, really quickly and explode in massive supernovae. So these blue stars that you're seeing are the most energetic, the biggest stars. Well, they've got some hypergiants and things, but in general, this is this is the sort of generally the biggest, hottest stars that we see, the blue ones, so the O's and the B's, which is kind of cool. They're much, much, much bigger, much hotter than the sun. So they're 2 to 16 times, so between 2 and 20 times the mass of the sun. Right? That's enormous, with surface temperatures between 10 and 30 for B-type stars. So honestly, these are hot and bright and putting out so much energy. So it's not a surprise, really, that we see this much gas. So excited to be friends with it.
Now, there's a question that I think Paul might be able to answer because it's to do with his image. And Imana wants to know, have the colours been enhanced at all?
Well, no. What you see, this is a combination of about 6 different filters. So light passes through each type of filter. So let's say L, R, G, B. So L for luminance, and red, green, and blue. And then the other filters are narrowband filters. So they are showing a specific bandwidth of light. For instance, O3, which is in the blue spectrum, and hydrogen alpha, which is in the red spectrum. So I've essentially tried to maintain the colour as it should be, and as it should look in a natural perspective. So no, they haven't been enhanced. Certainly, the data has been processed, but not manipulated like that.
Do you mind
Thanks.
if I just add something there? Because if you don't mind, basically when it comes to colours that we see with our eyes, obviously everyone sort of sees the things differently, but when we take photos of the sky, we're basically looking for, if we assign brightness from 0 to 10 in a particular colour. So, when you put red glasses on and everything looks red and it blocks out it only lets red basically into your eyes. That's essentially what you do with filters. So when you take multiple pictures in multiple filters, you're basically looking for the fluctuations from 0 to 10 in light, let's say, in that particular in glass, or red glasses, green glasses, blue glasses, yellow glasses, but a lot of other different wavelengths. And sometimes you can see an example of this if you have a look at any of the SOHO pictures, which is basically a satellite that orbits the sun and takes pictures in many different wavelengths, all the way up to sort of UV and all the way down to infrared. So these are actually just pictures in that one wavelength, like red sunglasses or blue sunglasses. And when we put them together, we have to make some educated guesses about variations of colour and what they actually look like. So when people say, has this photograph been doctored, or has it been changed, or have we edited the colours, it really does come down to an educated guess. And that's actually the same with photography on Earth. If you ask any photographer, has this image been altered, they'll say, from what? Or how do you mean? Because ultimately it comes down to, you're never ever going to produce what you see with your eye. And when you look out in the telescope with your eye at these objects, you certainly do not see the colours, because you need a camera and a long exposure for that, or stacking of images for that.
Actually, it depends on the diameter of the telescope. A really large telescope will show colour because it's producing lots and lots of photons all at once.
That's right. So for every photon that hits your eye, it's a piece of information, essentially. But most of the telescopes that we would be using, we typically don't see a lot of colour.
No,
we use 12-inch Meads, and we do see a little bit of colour in Jupiter and a little bit of colour in Saturn from some of the metropolitan areas of Melbourne, but not the sort of rich, deep colours that you see from sort of Cassini or Huygens probe. Yeah.
Well, where did our lovely image of Jewel Box go, Matt?
Oh, well, I was just going to show them exactly where it is.
Okay. So just I moved it off while you guys were talking. I moved it off your image, Paul, and jumped over to Matt over in Perth, who is actually live imaging at the moment. So he's going to, we're looking at Jewel Box cluster. So he's going to explain a little bit about where we're looking exactly. So take it away, Matt.
Well, welcome to the Perth Observatory. This is actually, I'm using stellarium, and we've got an actual skin for stellarium. So you can actually, this is the dome I'm actually in right at the moment. This is the very first dome for public viewing once we'd moved up to Bickley in Perth, in the Perth Hills here. But we're going south, and we're looking at the actual, the Southern Cross area right here. And just next to Beta Crucis, we've got this nice little cluster called the Jewel Box. And if I can just bring back backyard Nikon. Yes, good. That's working now. This is actually taken from our Nikon D810A camera, and we're using backyard Nikon just to take the photo. But this is a 10-second exposure at ISO 2000. Yeah, it's a really nice little cluster. It's called the Jewel Box because John Herschel looked at it and saw that it looked like jewels in the night sky. But it was actually discovered by Nicholas and Louise de la Caille from the Cape of Good Hope in South Africa in 1752. And he was the first to realize that the star known as Kappa Crucis was actually a nebulous cluster. Even then, they really didn't know what it was, but it's an open star cluster. So these stars are very, very young. They're between 14 to 16 million years old. So think of them as toddler to 5-6-year-olds for stars. And there's about 100 of them. It's one of the youngest known clusters, and you can actually, if you can you see the the arrow or the
yes, we can see your cursor, your reddish purpley bluey. Sorry,
yes,
reddish,
yeah. Okay, so right in the cursor. Yeah. So right here in the center are 3 really large stars, and unofficially they're called the traffic lights. And you can see we've got red, orange, white, and a bluish star right here. So that's where it makes up. This is about 6,400 light years away from us. It's a little hard to work out how far away it is because of the proximity of what's called the Coalsack Nebula, or the head of the emu of the Milky Way. And so that's obscuring some of the light, but it is actually about 20 light years across as well. So, you're seeing something that light has taken 6,400 years to travel from those stars to get into our eyes. So we're seeing it as it was 6,400 years ago.
Now, is it true that there's an asterism in the Jewel Box?
I think so. I think that was the from my knowledge, that's the traffic lights, isn't it? But
no, there's another one. There's
it
the shape of the A?
Yes, A. Yes, you can see right here that it does look like an A. Right here, right there. So, and you can actually see in the photo just down here, that's Beta Crucis. So we're using an ED80 telescope, so it's a wide field telescope. So it is very, very close to Beta Crucis, and you can see, and you can see it in binoculars as well. So, and even in even when it's really dark here, you can see it with the naked eye. So it's a really nice little object to show on the night sky too. We do get a lot of wows. I think this gets the second amount of wows after Saturn.
This is our Deep Sky section director's least favourite object. It gets stuck on there. It gets stuck on the scopes up at our dark sky site for hours on end. Because
I'm more of a nebula guy, but yeah. 47 Tucana is also really nice.
Absolutely, yes. Now, the next object on our list, and I'm not sure whether you'd be able to get that one while we have a chat about it, Matt, is the Southern Pinwheel, M83.
Yeah,
now,
let me just...
While we'll have a chat about it and see if you can get us a live stack of that while we have a chat about it. I know Paul's got an image of it here.
Centaurus
Paul, if you'd like to tell us what you used to image this, and then once you've done that, I might get Claire and Stefan to tell us a little bit about M83.
That's actually Centaurus A.
It is too. It's Centaurus A. What am I I'm looking at the viewing list. It says M83, but I've jumped onto Centaurus A. So let's talk about Centaurus A instead then, shall we?
Did you say you wanted me to talk now?
Yes, tell us how you imaged that.
That's right. We just had we're having a hailstorm.
Oh, you're having a hailstorm?
Hang on. I'm just going to turn up the sound a bit so I can hear you.
As Bill Lorry says, it's all happening here.
Yeah, it's all happening. Indeed.
But the host doesn't know the difference between M83 and Centaurus A, and Paul's being bombarded by hailstorms. All yours, Paul. Go for it. We're looking at Centaurus A.
We're looking at Centaurus A, a rather deep image of it. But there's some really interesting things about it. This is a giant elliptical galaxy. It's got a really high output in terms of
oh, we've lost Paul. He's frozen.
Oh.
Uh-oh.
Uh-oh. Now, Stefan, Claire, would you like to jump in while Paul's...
I'm more than happy to talk to you about what's really cool about this.
Yes, tell us what's really cool, because I know you're excited about this one, because this is down your rabbit hole.
It's definitely down my rabbit hole. So basically what's really cool about this galaxy, we think that, let me start again. In general, we think that nearly every galaxy that we see out there normally has a supermassive black hole in the center. So supermassive black holes are exactly what they sound like, super, so above, massive. So they're really massive, and they're black holes. And so what's really cool about these things, that they're between 1 million and 1 billion times the mass of the sun. So they're super massive, right? And they sit in the middle of these galaxies. And they're thought to be particularly extremely involved with the star formation and the formation and I guess the behavior of that galaxy over time. And what's really cool here is that this galaxy has a jet in the middle of it. So this has a supermassive black hole that has about 55 million times the mass of our own sun. And inside this galaxy, it actually ejects this material. So this sort of electrons and protons, so ionized material, that basically sort of spirals. So they think it's because of magnetic fields and the extreme environment down in this black hole, this jet comes out. And it's made of, as I said, protons and electrons, so charged particles. And when charged particles spiral, they're actually doing a type of acceleration because they're changing direction. And when charged particles change direction, they produce radiation. This is called bremsstrahlung, or braking radiation. And that's in the X-ray and radio wavelengths. And we can actually look at this in different filters, and it looks really different. So we can look at radio and X-ray, and we can actually see these jets, and it's absolutely incredible. And it's right in my my little wheelhouse, because I actually study a type of galaxy, a very, very active galaxy called quasars. So quasars have these supermassive black holes where they eat. They're voracious material consumers. They basically consume a lot of material around the black hole, and then they shine really brightly. So what's really cool about this galaxy, of course, is this jet. And then, of course, this jet, this energy causes heaps of starburst happening as well. So this is a really cool target to look at for me.
We actually have a photo of that jet, Claire, taken by Paul. Now, Paul's apologised. He's in the middle of a blackout now. It looks like the hailstorm's more severe.
Oh, in the black hole.
Yeah, so we've actually got a photo of the jet coming out of this galaxy, which Paul has taken. I'll show that a little later on. Anyhow.
That'd be great. Now, this is an image taken by Andy. Andy, what did you use to take this image of Centaurus A?
Okay, I'm just having a look here. Yeah, it was a 6-inch Newtonian. It's a Skywatcher Newtonian with an old Canon 450D, and I did 22 5-minute shots of this and stacked. Yeah, so it's about, how long was that? 2 5s, 100. Yeah. It was a few hours anyway. 1 hour 20. Yeah, that's the thing. I can tell you it was 300 seconds for shots and just 22 of them. But yeah, it's just a like an old Canon, 12-year-old Canon on my scope. But I'm lucky here. I'm in Border 1, so a very little Border 1, pouring with rain, windows shaking at the moment.
Pretty poor weather out there at the moment for most of us.
Yeah,
Now-
we normally get blackouts, so don't be
No,
surprised.
this is Anne Marie's image. Anne Marie, your images are some of my favourite. I love seeing them pop up on the Astronomical Society's closed astrophotography group. It's always good to see your images pop up. This one is another one of your amazing astrophotography images. Tell us a bit about this one.
Thanks, Mark. This one's taken with my reflector, which is a 250 1200 focal length. It's 5.6 hours, and it was shot in lume red, green, and blue. And yeah, they're all 2-minute exposures. I'm also lucky. I've got Bortle 2 skies here, so we are very lucky.
Now, I'm not sure what Matt's got happening over there. It looks like he's moving the telescope. I can see some panning happening. So we'll come back to him shortly. We'll jump over to Lee's image of Centaurus A. And Lee, you want to tell us a little bit about your image of Centaurus A?
I'm trying to remember, actually.
You should keep your data on hand.
Well, the data's all there. I just, yeah, it's been a while since I took it. I think I'm trying to, what are the dates on these? That was, okay, it was only in May, actually. So that's using the Edge HD8, Celestron Edge HD8, which is an 8-inch Schmidt-Cassegrain telescope. And it's a mono camera with, that would have been luminance red, green, and blue filters. So taking a whole lot of shots in fact, I used IR infrared for luminance, and trying to think how many. It's probably only a couple of hours worth, which is why it's not actually the best. You can see quite a little bit of noise in the image, but I think it was not long after I had a few adjustments to the to my guiding. My guiding's not actually that good at the moment. So I have to take a lot of shorter images. So the likes of Van Marie and a lot of the others end up getting these fantastic shots where they can get 2, 3, 4, 5 minute shots per image. I sort of suffer with 30-second shots and many of them, and just stack the hell out of them. So yeah, it's not the best image, but it's I just love just mucking around with the post-processing a lot and just getting different results out of it. And you can certainly see the effects of this, like the dark bands on the outside and that sort of bright core, which as Claire was saying is most likely a quasar, I think is.
So that brings me to a question we have that I'll throw at Claire to start with, and also Stefan to follow up with if he wants to. Both of you don't have to answer this if you're not sure, but I'm hoping you might. James wants to know, was Centaurus A the galaxy some astronomers believe the radio waves were from extraterrestrials?
I have no idea. Do you know, Stefan?
Stefan, do you have an answer for that one?
I think the dead silence is a bit of a giveaway. Not quite sure. Yeah, I'm not sure.
It's a good one. That's one for us to have a look at. If anyone else knows anything about that, let us know. That's for sure. Now we have another question. This one's for the astrophotographers. When you are taking lots of shots over a few hours, how do you order the different filter settings? So when you're talking about red, green, blue, luminance, hydrogen, alpha, and oxygen, and whatnot. So how do you do an imaging run?
I guess I can answer this one.
Yeah, go for it. Yep.
So when you get to a certain level, you strive for something that we call automation, where you don't have to physically, take the filter out of the filter slot. We have equipment called an electronic filter changer. So we've got all of our filters in this big rotor, and we can control that with our computer, and we can select which filter we want to image through. Now, which filter we image first sort of depends on where the object is in the sky. Because of some sort of complicated physics, blue light tends to scatter a lot more in the atmosphere. And so we tend to image through our blue filter when the object is at the highest point in the sky, when there's the least atmosphere to interrupt it. So the way that I tend to image is I tend to image red when it's lower in the sky, and then green, and then blue when it's at its highest point in the sky, and then green, and then red going down again. But of course, you can select any sort of way that you want.
Now, we have, Matt has been able to get through the clouds a live stack of Omega Centauri. If you'd like to have a chat about to us about Omega Centauri, Matt. If you can find the unmute button. Where did we go? Whoa, here he's doing his thing. You might need to unmute, Matt.
Sorry. Sorry about that. Okay, so we're going from the Southern Cross, expanding out a little bit. And if we have a look, we can really cool thing. So Stellarium is free, and you can actually get it, and you can go back in time, go forward in time. You can show where the actual catalogs are if you don't know. So we're actually looking at the back of the Centaur. So there's two Centaurs. There's one with the spear, and then there's Sagittarius, the one with the arrow, which is in the center of the galaxy, in the Sagittarius arm. And we're looking right here. So this big ball of stars. Actually, this is the largest of the 120 or so globular clusters in our galaxy. There's the biggest one we've actually ever seen is somewhere in around Andromeda, Merrill 2, I think it is. It's about 250 light years across and has about 20 to 25 million stars. This one comes in at about 10 million stars, and it's about 150 to 170 light years across. So it is quite nice to have a look on a night sky tour. I prefer 47 Tucana, the second largest around the southern hemisphere, or second largest of the actual globular clusters. Thankfully, in the southern hemisphere, we have both of them. So all the best stuff is in the southern hemisphere. We might not have a pole star, but all the best stuff is here. It is a little bit fuzzy because we, even though it's partially clear, we've got some pancake cloud. Yeah, so there's self-migration as well. So what you can actually see is the little stars that might get formed in the center, they actually get kicked out to the outer edges. And if you get what's stars called blue stragglers, where you get stars that can collide together, they can actually fall into the center of the actual cluster there. These guys are like an active retirement village. They're about 12 billion years old. So they're really, really, really old, but still very active.
That's a very good description. An active retirement village. I like that.
Yeah.
Now, I think
they've actually found... Sorry, I think they've actually found a couple of pulsars in here as well, or that might be 47 Tucana.
Oh, it's above my pay grade, that one.
Yeah.
I'll leave that one. The answers to that up to Stefan and Claire and the others if they know the answer to that. So now I think Kim is trying to bring up some images of Centaurus A and Omega Centauri as well, taken by some of the ASSA members. So we'll try and bring those up to you shortly. Well, we've got that. I think we've got one from Lee that Lee has taken of Centaurus A.
Oh, I did have. Hang on. No, Centaurus A. That was what we were on before.
Sorry, that's Centaurus A. Omega Centauri. I've got Centaurus A on the mind at the moment because I've seen quite a stunning image in a chat group that I'm just trying to work out if Anne-Marie took that image or not, and if she did, I'd really
definitely not. That's a Hubble one.
It's a Hubble one.
Hubble.
Okay.
Yep.
All right.
We can't shoot
for the moment.
We can't shoot that like that from Earth.
I think that's the one that includes the X-ray. In fact, also.
That's correct.
Yep. So this is Lee's Omega Centauri. Tell us a bit about this one, Lee.
Oh, look, that's it. it is significantly bright. So that's let me see. I did have the details on this one. 40, 20. It is. I'm just trying to calculate this. That's 20 minutes of each red, green, and blue, and again infrared to get that. And I think even then I had to sort of dull it down quite a lot by the time I had the eventual the end image. Then it's just a little bit of processing in Photoshop just to clean up because you still get a lot of noise, even pretty much everywhere at some point. But I reckon I've got another one of it somewhere which is a bit more orange, but and even here you can see some of the blues are a little bit blown out, but I still like the fact that you can specifically see some blues and different coloured ones in various areas to denote the different stars.
And we've got one from Andy here as well. So Andy, tell us a little bit about your image that you took of Omega.
Yeah, this is a 30-second image, just with my scope here. I put my scope up here just to it's just a single 30-second image with a DSLR, but zero light pollution, so there's nothing to but you can see this with the eyes. You just walk outside and within a minute or two you look up and you can see a bit of a fuzzy patch. It's quite fuzzy, but within about half an hour it really stands out. But it's an easy object to find just by looking up in zero light pollution, of course.
Now, Claire, she's running back. I can see her off screen. Stefan and Claire, do you have anything to add to what we've been chatting about with Omega Centauri? We do have a question, and this kind of relates to this, so one of you might be able to answer it. Has a nova been discovered in a globular cluster?
So, if you don't mind, Stefan, I'll just jump in and then you can add anything I've missed. I'm sure I missed something. Globular clusters are really cool. So if we think about the structure of a galaxy, you normally have the center with the supermassive black hole. You have sort of the stars, which make up sort of its disk and a bulge. And then you have this sort of halo around the outside. And then outside of that, you have all this dark matter. But sort of in that halo is where we see these globular clusters, which is what Omega Centauri is. It's a globular cluster, and it's a glob, right? And it's usually symmetric, and usually all the stars are about the same. I'm getting a lot of feedback. Is anybody else getting that?
I can hear that. I can hear that feedback. Yes.
Okay, I just would hate for that to be. Let me try that. There we go.
No, I can still hear you. You weren't having feedback before, but now you are, which is quite interesting.
Everyone, if that's me, I don't know how to mute everything. That's really strange. I'll just stop talking really loudly. Does that help?
That's all right. I think I know what it was. It's all right. Try now.
Oh, okay. So it wasn't my fault. Okay,
no.
Excellent. Okay, so
Andy wasn't muted.
Oh, Andy. Globular clusters sit in this halo around galaxies, these globs of stars, and they're some of the oldest stars in the galaxies, and that's actually kind of why they're all red. So these are really, really old stars sitting there all together in this sort of group. What's cool about Omega Centauri, of course, is actually that when they look at it, there's actually groups of populations of stars in there that aren't the same age. So that's a little tidbit for you. But generally, we know that these stars were probably formed very early in the history of the universe and also in the history of the galaxy itself, because they don't contain very many other elements apart from hydrogen and helium. And if you're an astronomer, I would say they don't contain any metals, because to astronomers, we have hydrogen, helium, and then we have metals. So these stars actually basically are only hydrogen and helium mainly, which means that they really were some of the first stars, not the population 3, which some of you might know about, but definitely some of the earliest stars in the galaxy's history and the universe's history. Stefan, what have I forgotten?
Yeah, I guess I can add a little bit. Just briefly, as a person doing chemistry, hearing astronomers refer to everything except for hydrogen and helium as a metal, it hurts. But I've got to say, so with globular clusters like these, it's easy to see them as the picture that you see in front of you. But what I think is beautiful is when you try and imagine this giant collection of stars as it really is in motion. Of course, all astronomical bodies are in motion, but because of the distances involved, we don't see this motion on the human timescale. But try and picture this kind of object moving in fast forward. This is an absolutely chaotic bundle of stars, zooming in and out like a hive of bees gone crazy. And there's one story that's always stuck with me that I read. It was a sci-fi book about a planet surrounding a star within a globular cluster like this. And just try and imagine what it would be like. Forget the fact that, planets don't typically form around stars in globular clusters just because of how chaotic the system is. But just try and imagine what it would be like to look up at a night sky from within a globular cluster. You probably wouldn't have night skies to begin with just because of all of the light, but I think it would be a spectacular sight.
And to answer that question about nova in the globular cluster, so the word nova comes from the word new, I suppose, in Latin. So nova means new, and it's not actually the same as a supernova. So a supernova is a star at the end of its life, a very, very massive star that basically layers collapse because it can't hold itself up anymore, and those layers send a shockwave down, and while the material's falling, the shockwave is rebounding off the core, and that causes this big explosion. So that's a supernova. But that's actually not what a nova is. A nova is basically a star that actually just for some reason just increases in its brightness very, very rapidly and then goes back to being a happy little star. And we're not always sure about why they happen. It could be to do with accretion onto the star or binary stars and things like that, and stars sort of interacting with the environment around them. And there has actually been some novas discovered in globular clusters before, and so up, so early pre-1990s, and that's certainly an ongoing search for these novae in globular clusters.
Okay, so we did. Thank you very much for that, Claire. That's a really good answer to the question. And Stefan, thank you for your responses there as well. We had the moon for a second there in the cloud, but I'm going to blame the two of you for taking too long. So what we're going to do is jump to Trifid Nebula. We'll have a chat about Trifid Nebula, and if the sky's clear enough for Matt over in Perth to get the moon again, we might jump back to a live view of the moon. But for now, I'm going to bring up Anne-Marie's image of Trifid Nebula. Now, this is, I love this object, and it's one that I am very, very feverishly trying to attempt to image with my phone through a telescope when we get some clear skies. But Anne-Marie, could you tell us a little bit about your image here, how long these exposures are? Because usually your runs are hours long. What's involved in this one?
This one's not.
No?
This is actually, no, it's only 3 hours, just over 3 hours. I wasn't prepared for this one because it wasn't on my list. But yeah, 3 hours and 22 minutes. But this one is actually a combination of both of my scopes. So the ED80 refractor as well as my my reflector. So, and I've combined what I took from the refractor last year and the reflector this year and combined it together. And it's just 3 hours and 22 minutes. So it's just all in RGB. Oh, there is a bit of HA there, and that's on the old scope, the refractor, and a bit of O3 in there as well. So okay. A bit of everything.
Yeah. We're going to have to jump back to it because the clouds have parted and the moon is up live on on Matt's screen. So this is a live image of the moon from Western Australia, from Perth, Perth Observatory.
We're looking right here, and let's have a look.
Let's have a good look around. Now, Stefan, I know you know a bit about the moon, so tell us a little bit about what we're looking at the moment.
Well, yeah, I don't exactly know where to start. I'd hope that everyone on Earth would know what this is. This is our satellite, our twin in the sky. Yeah, it's the only major satellite of Earth. and it's actually one of the largest satellites in the solar system. I believe there's only one moon. I think it's Callisto of Jupiter that is bigger than the moon. So it's actually quite special that we have such a large satellite. But yeah, I mean, what can I say? I think everyone in the audience probably knows what the moon is. Yeah.
Yeah, we've got so there's Ganymede as well, and which is a moon around Titan. Around Jupiter, and then there's Titan as well, and Io just beats us. It's about 1,000 kilometers wider. So yeah, I think it's still relatively big. You can actually fit it in between Perth and Sydney. So it's a decent sized moon, which is great because it controls all the tides. It allows us to allows for the Earth to be in a nice stable rotation, so it's not drifting all over the place. And as it goes, there it goes. So yeah.
So it's actually
I guess there's
satellite.
Sorry, Claire, you go.
To its planet. So I think that's maybe what Stefan was saying, that it's the biggest satellite relative to its planet's mass. And then there are it's the fifth biggest just general satellite. But I mean, in terms of how much mass, I guess, or the size of the moon versus the size of the Earth, it wins in the solar system. Yeah.
Yeah.
One also thing that you may have heard of in the news recently has to do with the moon's wobble, or essentially it's a difference in the orbit of the moon. And in the year 2030, there was just a paper released by NASA where they were basically explaining that around in the 2030s, the moon's wobble, or some precession in its orbit, I think Claire can probably describe a bit more about that, is going to basically coincide with rising sea levels. And NASA thinks that this basically wobble may lead to extra high tides and lead to some flooding. So
I think you've summed it all up. Now, is there any particular points on the moon right now that we're looking at that you guys can identify for us?
Yeah, so just below the center of the screen, I believe that's Mare Tranquillitatis, which is one of the, it is the location of the first moon landing of Apollo 11. And also towards the left of the center, there's this large mountain range called Montes Apenninus, or the Apennine Range, which is home to Mons Huygens, the largest single mountain on the moon's surface.
Okay, so what we're going to do quickly is jump over to Kim before we go back to the Trifid Nebula. He's been nagging me in the chat. I'd forgotten. A lot going on at the moment. He's got some images of Centaurus A with the jets. So Kim, it's all yours. You're on mute.
How's that?
That's better.
All right, so here I've got a map of the Centaurus region. You can see the Southern Cross and the pointers on the left here. And if you follow this line up from the pointers, about the same distance up, you get to the globular cluster, Omega Centauri. Go a little further, you come to Centaurus A, and that's how you can find it in the sky. So I've got a number of objects shown by these green squares that I've got images of. So I'll just talk to Centaurus A for now.
Yep.
And this is an image I took just from my backyard. It's a very basic image. It's a single shot. You see it's actually quite noisy. It's a 3-minute exposure, just done with a very small refractor. But as you add more and more images, the image actually becomes a little less noise, and there's only 20 images here now. So it's about a 1-hour exposure. And you can adjust the dark point quite easily just to get rid of the grey. So these are straight off the camera. These are actually the preview images, not the final images, right? So they're a bit ordinary, but they're very good for outreach and having a quick look around the night sky. So as you adjust the dark point, nothing's changed here. It's the same image. I've just got rid of the grey. Now, on top of this image, which I took with a very small refractor, Paul Hazy took another image of this galaxy that you saw earlier, and I've superimposed it on this image in the next slide, and that's it shown there. You can see the effect of much, much longer exposures. Now, I had a 1 hour exposure here with a very small scope, and I don't, off the cuff, I don't remember the size of Paul's scope when he took this image, but you can see there's a lot more detail, a lot more stars, and that was a total of 80 hours of imaging, which is phenomenal, right? And this is the image again, and you saw it earlier, but something you may not have noticed earlier is there is a jet. There's a hydrogen alpha jet running along the bottom of the lower right here, that red line. I don't know if you can see that.
Yes, I was just going to say, you can see a little red line down to the probably what is about 4:30 on a clock. If we're looking at
where I've got the cursor, if you can see my cursor, it sort of runs down through there.
No, we can't see the cursor.
Oh, you can't. Okay, so it is.
Yeah, it's about sort of 4:30 on a clock. There's a little red sort of sputtery line of redness. I don't know if you can see that, Claire. That red line there, that's the end of the jet. Is that not?
That's where it is. Yeah, for sure. I think Paul took at least 10 or maybe even 20 hours just in H alpha to try to bring that out of this image. So it's quite a phenomenal deep image taken by an amateur astronomer, right? From a dark sky location, right? So
it's impressive the amount of hours that have gone into that. 80 hours.
80 hours imaging
to get that photo.
Yeah, versus one hour.
Versus 1 hour, yes. Look, the 1 hour is still good. Don't get me wrong. But that.
By the way, that's the first time I think I've ever imaged that galaxy. So yeah, I was quite happy with that.
I'd be happy with that too.
So I did have Omega Centauri. I know there's been a bit of conversation about that already. Yep. And again, this is a very. I don't have the exposure details. This is just my scope in the backyard, and that's Paul's scope. And he had a much tighter shot on this. But the next photo shows that region of Paul's just across the full screen. You can see all the stars present in this cluster. This globular star cluster. So it's quite a spectacular image. I don't have the details with me. I was hoping Paul would be back. I just got a message from him saying he's definitely not back on tonight. He's lost power big time.
He's absolutely lost power.
Tomorrow morning. All right. So I do have other stuff. I'll get to that later. But yeah, I thought I'd show those two before we got too far ahead of ourselves.
That's all right. Well, let's go back to the Trifid then for the moment. Yep. And Stefan, Claire, take it away. Fight between the two of you to see who wants to talk about Trifid Nebula and explain a bit about this one.
I guess I can start. So this is a really spectacular example of all of the three main types of nebulae that we were talking about at the start of this stream. So we've got the blue reflection nebulae, the pinky red emission nebulae, and then the dark brownish black absorption nebula. So this is a real treat to image for astrophotographers. It's a really nice bright target, really colorful, a really good one to go for. So the Trifid's located in the constellation Sagittarius, right next to the Lagoon Nebula, and it's around 42 light years in diameter. So this is quite a big cloud. It's around 4,100 light years away. So Claire, do you have anything to add?
Sorry, I was just having trouble with my mute button.
I was just going to say, pressure's on now. It's like over to you, Claire.
The Trifid Nebula is actually really kind of cool. You might have seen some of those when you see that zoomed in picture where it looks like this bug. It's kind of got this like dusty cloud head with these little antennae. It's one of my favorite pictures, actually. There's a Hubble picture of M20 or the Trifid Nebula. And basically it's massive star-forming clouds with gas and dust and then just illuminated in spots. And so at the end of these stalks is actually, they think that there's two stars actually brightening up that region. But you can kind of definitely get the idea here when you look at this image and also the zoomed in image of this sort of bug looking thing of the fact that these stars actually do need these cold, dense, dusty environments to light up, and once they do, they just illuminate all of the gas around them. So these are the stars. You can see these stars here just putting out all this UV light and exciting all of the atoms around them, which pushes the electron up a level, which I think Stefan said before, and then when it drops, it releases this characteristic color of light, which is absolutely beautiful.
Okay, so now I think Prison Break, that's his name now, Lee's now going to be known as Prison Break, is trying to find that image that you were talking about, Claire. So while he does, Ashley wants to know if this has been recorded. Ashley, yes, this will remain on pretty sure it'll remain on the Perth Observatory Facebook page, the Astronomical Society of South Australia Facebook page, the Astronomical Society of Victoria's Facebook page, and our YouTube pages as well. So you will be able to watch this back and pause it and take notes and whatever you might need to do once we finished. It's not going anywhere, that's for sure. And then Chris from Darwin, hello Darwin, wants to know how long it took some of us, those of us who use PixInsight, to become confident using PixInsight. So this is for anyone who has, of our stream team, who has used PixInsight. I use Astro Pixel Processor myself, so I've never used this program. Anne-Marie, have you used it?
I use PixInsight.
Yep.
It probably took me 6 months to actually feel comfortable with it, and probably another 12 months to actually think I'm starting to get somewhere, but there's still a lot to learn. So I've been using it about 18 months now.
Lee, do you use PixInsight?
Yeah, I do. I think a lot of the processes it does similar to other, a few other programs around. It's more the interface that I think confuses a little bit, because little things like I use multiple monitors, and you might be able to have your images on one monitor and you go and move them up there, and then but you open up a script, but the script will only run on the bottom monitor. You can't drag it to another monitor. So it's got little bits and pieces like that sort of can be frustrating. But as Anne-Marie said, it's something that just takes time, and then you get used to using it, and you get used to those little they're not really failings. It's just it's how it's been written. But yeah, so it's much like with things like Photoshop. You can probably open it up, and within 10 or 15 minutes after following a video, on YouTube, you'll be able to know how to do masking and cut levels and curves, and eventually you'll get more proficient at doing a bit more than that. And the same thing goes with PixInsight. It doesn't take too long to be able to start using it at a basic level. It's probably going to take years potentially to get to that really, really professional level. But I think only a short time to get to the point where you can really start to post images in members forums and things like that, and Astrobin and things that people, really get the wow factor out of.
Now, I think, Lee, what have you got there? This is not the image of Trifid that that Claire was talking about.
No, that's sorry, you're up. No, that was the Centaurus A. I thought that's what you're
Centaurus A. No, we're talking about Trifid. So we're talking about Trifid. We'll give you a little bit more time to dig it up, and we might start to have a look at our next object. I think I saw some people earlier with their images of Markarian's chain, which is one of my favorites to look at visually. So I'll give the guys a little bit of a few moments to get their images of Markarian's chain up. In fact, Andy's already got his, and he's on the gun. So, Stefan, I know you know a little bit about Markarian's chain, and I love the way you say his name. I can't say it the way you say it, but I do prefer your version of it.
Markarian.
Markarian, that's it.
I don't know if that's right. Look,
Yeah, I've always known
that's
it as
just how I say
Markarian's
it.
chain, but I could be wrong. It's highly likely that I'm wrong.
Yeah, so this is a really, as someone who hasn't encountered astronomy before, if you're looking at this picture, you may not really see anything special about it, right? It just sort of looks like a bunch of stars and a few fuzzy blobs. But this is actually one of the most spectacular types of targets. It's what we call a galaxy cluster. So all of these sort of fuzzy blobs that you see, this sort of line of fuzzy blobs, each one of those fuzzy blobs is a galaxy in and of itself, containing some, billions to perhaps trillions of stars. And so this Markarian's chain is a cluster of approximately seven galaxies that make up part of the Virgo supercluster. They're located around 50 million light years away. So the light that was captured in this image left those galaxies around 50 million years ago, long before Homo sapiens walked the Earth and even our distant hominin ancestors. So this chain of galaxies, Markarian's chain, is now named after an Armenian astronomer called Benjamin Markarian, who discovered that they share a common motion and are thus linked in the galaxy cluster. He discovered this back in the 60s. And so analysis of some of the spectra of these galaxies, particularly M84, showed that within a region of around 25 light years in this galaxy, there's some gas moving at around 400 kilometers per second, which indicates that there's a supermassive black hole within this galaxy. Now, M84 is actually the galaxy right at the top of the chain. I'm not sure if it's that one there. It may be. I think it's the one just above it, up the top. Yeah, that's M84 there. But yeah, so this is a cluster of galaxies, all millions of light years apart, yet still interacting through their shared gravitational force.
Now, I know in the chat, we've got a little secret chat that nobody else can see. Andy's saying that this is 120 minutes of unguided imaging on Markarian's chain, so 2 hours worth of data on Markarian's chain. Now, I noticed that Kim has got an image of Markarian's chain as well that he has taken with a satellite ripping through the middle of it. Tell us a little bit about your image there, Kim.
So this is actually this is the first ever image I ever took of Markarian's chain. It was taken from, unlike a suburban area, I took it from Stockport Observatory, which is a Bortle 2 sky site, where we have our main observatory in the society. This is a 2-minute exposure only, and you can see it's a single exposure, lots of noise, and then there's this satellite trail through the image as well. And I took a few more images. This is, again, with an 80mm refractor that I showed earlier. Now, after you've taken about 10 and they've been automatically stacked, you can see the satellite trail starting to wash out, and that's one of the features that washes out as you average the images. And you'll see also the background noise has reduced considerably, and all I do then is just adjust the black point just to make the image like that. I don't use PixInsight, don't even use Photoshop. It's just very basic stuff, and these are just the preview images. You can just make out the satellite trail still, but for something that took, say, 20 minutes, this is something you can show at a star party and to others very easily with just a very basic bit of kit, although it is a bit pricey. And I've counted about 40 galaxies in that field of view, which for a 20-minute exposure I thought was pretty impressive. So yeah, that's all I had on that one, Mark.
Just a quick glance there, I can see what I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 without really having a good look. I can see 23 galaxies in there. A lot of little faint fuzzies in there. And we've got an image of Markarian's chain from Anne-Marie. It's a little bit more of a zoomed in image. Anne-Marie, would you like to tell us a little bit about this image?
This one's only a part of the Markarian chain, as you can see.
The top part, isn't it?
Yeah, because obviously that's all my reflector can actually take. This particular one is only 2¼ hours, and once again 2-minute exposures in lumens red, green and blue.
I can still
Processed
see,
in PixInsight.
I can still see 16 galaxies in this view as it is. If you look close enough, you'll see some really tiny, faint objects in there that kind of look like dull stars, but they're not. They're actually galaxies. In fact, if I really, really look, I can probably see another 17, 18 galaxies. Claire, did you have anything you'd like to add about Markarian's chain and this collection of galaxies and why they collect like this, maybe? I don't know.
Well, I was just going to say that for those of us that, well, I mean, Stefan mentioned before that they're part of the Virgo cluster. So you might think of galaxies as being enormous, you know, like 100 light years across for the Milky Way, for example, 100 million light years across for the Milky Way. I think that's right. And basically they've got a lot of stars, but galaxies actually, if you take a step back, they're like marbles, right? There's a lot of galaxies and they actually gravitationally cluster in together. So some of you might know that galaxies cluster into groups, and our galaxy, the Milky Way, is clustered in with 54 galaxies in something called the local group. And that has like the Triangulum galaxy, I think it's Andromeda, a couple of Messier objects as well in this group. And that's the local group. And then this is actually a little cluster of galaxies as well called the Virgo cluster. And we are all part of a really, really large cluster called the supercluster, which is called the Virgo supercluster. And when we look out into the universe, we actually see other galaxies arranged in this way. So we see superclusters, we see little clusters that gravitationally bound that actually have a gravitational effect on each other. And then you look into galaxies and you see their stars. And then, you know, if you look even closer into stars, you see planets. So it's kind of interesting that we keep seeing this sort of structure. It's almost like cutting up a piece of material and getting right down to the atomic size. The structure just keeps repeating. And in fact, if you step backwards from superclusters, you eventually get into these amazing ribbons and filaments and void structures of the entire universe, which is absolutely fascinating. I think that we can sort of slice it smaller, we can slice it bigger, and we just keep seeing similar patterns of clumping repeated over and over again. So slightly sideways bit of information for you, Mark.
Sideways to get to the answer is still a good way. And that's what we're going to do now. After that lovely explanation, we're going to jump to, you were talking about the Hubble palette image that you want of Trifid. So we've got it. But once we've had a chat about that, Kim's got an image of the dark Doodad Nebula that we will bring up. So we'll jump across to Lee's version that he's found of the Hubble Trifid that you were talking about. It's a very close-in cropped image of Trifid.
Yeah, so this is one, but in fact, I like the other one slightly better. But you can see at the top of, actually, it depends on which one you want to look at first, Claire. So you've got this bit here, which is actually that there.
That's the one. That's my favorite.
You know, I think this looks
so
like
cool.
That's got to be a dove, doesn't it?
A dove. Wow.
Dove.
Oh no, I see a bug with antennae, like a slug, basically, or a snail.
Oh, here I do for sure.
Yeah.
That definitely is.
So at the top of those two little antennae, actually, the two finger-like jets, right? They actually they think that they're forming new stars at the top there. You know, that's all that gas and dust and the cold molecules out there. And then, you know, what I think will be really cool is if there are little stars at the top of those antennae, and then they just sort of like light up, because they'll blow away some of the gas and dust, but they'll be there those like shining horns. And who doesn't want those?
Little eyes at the top of a slug.
Yeah, exactly what they look like. It's one of my favorite things in the sky for completely mature reasons.
There's nothing mature about astronomy. It's all fun. If it's not exciting or not fun and not eye-opening, then there's not much point in doing anything, really, is there? And that's the one thing I love about astronomy, is that everything we do is exciting. Everything we look at is inspiring. Whether we can reproduce those same images or not doesn't matter. It's engaging, it's exciting, and we're all learning something.
I should also say that, sorry, the scale of those antennae things, they are 3/4 of a light year long, approximately. So, you know, if you wanted to go in your spaceship at the speed of light, which don't talk to me about physics, let's just pretend we could, that would take us 3/4 of a year. We can't go that fast. We can't even go 1% of that fast. So they are absolutely enormous, and yet they look tiny. And also in this image, this particular image, which is of course the Hubble image, you could actually see colours here representing the atoms that are in this cloud. So you've got hydrogen and sulfur are the red colours. So there's got a lot of sulfur in it, this cloud. And then we've also got some green colours in there, which is actually oxygen, which is really, really fascinating, I think, if you have any interest in the origins of life and astrobiology as well.
Look, talking about the speed of light, if anyone saw the ASV's Facebook post earlier with Colin Carpenter, speed of light is almost as fast as his mate's V8 Holden. So it's fast, but it's not quite that fast.
Is that the one with the fully sick intercooler, or?
No, not sure. Don't know if he had the fully sick intercooler. Now we're going to jump across to Kim. Has got. He's going to have a chat to us about the Dark Doodad Nebula. One of my favourites.
Thanks, Mark.
I love the name, Kim.
I think Claire's going to jump in on this at some point anyhow.
I'm sure she will, and I hope she does.
Right.
I hope Stephen does as well.
Right. Okay, so what I have here again is a map. You can see the Southern Cross in the centre, the pointers, and down below the Southern Cross in the constellation of Musca the Fly, just off that star there, is a globular star cluster called NGC 4372, which one night I decided I'd go out an image, and I took one image, and then I took 20 of them. And as I was taking this, I noticed that there was this dark area here where there were no stars, and I wondered what that was. But you do notice that the globular star cluster here, it's got all these nice golden coloured stars, and there's the star that was shown in the image previously on the map. But what was this thing? So I did a bit of looking around, and this is what I found. This is an image from an Italian astrophotographer, Marco Lorenzi, and I believe he travels to Australia or has travelled to Australia. And he actually took this image from the Warren Bungles. And I'll show it in full, but you can start to see there's something happening there. There's something dark, not quite stars. And in the next image, you'll see what he's got. And that's it. That's your Dark Doodad. And that image got him an astronomy picture of the day, an A-pod, and taken from the Warren Bungles, I believe, at the time. But yeah, you can see the globular cluster there on the right, and there's the Dark Doodad, which spans about 30 light years and is about 700 light years away. So it's quite a large structure in our part of the Milky Way. So yeah, I was quite impressed with that. And one day, from a dark sky site, I'll go out and try to take an image like that versus the other one, which I took from my backyard in suburbia. Yeah.
Yeah. Stefan, Claire, do you have anything to add about the Dark Doodad Nebula?
Yeah, I guess just briefly. So this is one that we were talking about at the start of the stream. And like I was saying with these dark nebulae, to me, they always really pop, and especially an image like this. Now, the Dark Doodad itself is only around 700 light years away, whereas the globular cluster in the back, NGC 4372, is actually 19,000 light years away. So the Dark Doodad really is just sitting there in the forefront, while all these stars in the background are just really, really, really far away. And so, yeah, the Dark Doodad, it's this big cloud of cold molecular gas, so cold that atoms are starting to cool and form into small carbon-containing molecules. And eventually, over time, these clouds will collapse further and further and give birth to new stars. So these are sort of like stellar nurseries in the making.
I can just add a couple of things, probably just sideways things again. I would say that it's kind of amusing. Whenever you look at pictures of nebulae, like dark nebulae, I think the tendency for human beings at least, is to say that, oh, where it's dark is absence of light and that there's nothing there. And in fact, gas and dust is sort of ubiquitous. This interstellar gas and dust is everywhere. It's just that in these pockets, it's just so thick, as Stefan said before, that the light can't actually get through. It's absorbed. And so we really only see it because of the backdrop of these brilliant backgrounds of stars. And that's really the only reason we see it, is because it's thick enough to actually not have the light go through. And there was actually something else I was going to say. It's completely escaped my mind. Oh, no, that's right. So you might also think that because stars are really hot and they're burning energy, that they actually need to have a hot environment to form. And this is actually not correct. Even though stars do definitely need to be dense enough and hot enough to actually force the interior of atoms, so nuclei together, they actually have to have a cold environment for these molecules to actually, for these gases to come together and form molecules. Because another way that we think about temperature is actually the speed or the velocity of particles in a gas. So when we heat up particles in a gas, they move around a lot and they bang into each other a lot, so they don't actually come together. So we need a gas cloud to actually be cold enough that these particles can come together, and gravity can actually kind of, or intermolecular forces can actually bring them together and keep them together to make these molecules until they can actually start gravitationally attracting other pockets of molecules. And so that's why we actually really need it to be cold, and we need it to be dense enough for these particles to actually have instances where they come into contact with each other. Once the star actually ignites, it actually blasts away a lot of this material. And there's a really sort of fine tipping point there where if the star hasn't actually got enough material to make itself, it kind of fails and becomes sort of like a brown dwarf, I suppose.
I hope that answered everyone's questions. I'm standing here going, whoosh, over my
Also,
head.
I'm going to say to Prison Break, you're right. Doodad was not the person that discovered it. The person who actually discovered it was, I'm not even going to attempt, well, it looks like the word A, but it's A-A-G-E, right? Sandquist? Yeah.
Sandquist.
Yeah. Sandquist in 1977. However, Doodad, you're right, was an American in the 1986s. Dennis DiCiccio? Chico? I don't know. I need to probably brush up on my...
Chico.
Chico?
Chico.
Chico.
All that operatic singing I did a long time ago is sort of paying off. Anyway, Dennis DiCiccio in 1986, he's like, oh, it's a doodad. So he was American because, you know, that's how they all speak, apparently.
I do love the accent.
But yeah, he was basically in Central Australia. And he's like, you know, it's a whatchamacallit, it's a doodad. So unfortunately, that name is stuck.
Wow. You know what's funny about that? We have some comments. Doodad, is that a thing? Yes, it is.
Yeah, it's
Where is the like Thingamabob Nebula? Well, Adam, I'm pretty sure the Thingamabob Nebula is with the Doodad Nebula, and it's in the whatchamacallit drawer with all of the Thingamabobs. And the Ujo Watsits.
Top 20. Hasn't anyone watched Little Mermaid in a while?
Was that? No.
Little Mermaid.
No, I haven't seen Little Mermaid in a very long time.
In the song, yeah, I know what you're talking about.
The Doodad is with the Thingamabobs in the whatchamacallit drawer.
I have to just add on that, astronomy, astrophysicists and astronomers, particularly when they're naming programs and telescopes and things, do like to come up with some really questionable acronyms. So there's things like GADZOOT, which is, you know, they've tried very hard to make that fit a gallium detector or something. So, you know, Thingamabob might be a thing at some stage. It might be the Grand Thingamabob telescope.
There you go. Challenge accepted. If any one of us finds something new in the night sky that nobody has seen, it is either a Thingamabob or a whatchamacallit. All right, that's it. That's what you're going to name it. Now, we have a question which is from Bill, and I'm pretty sure Bill probably already knows the answer to this. Is the dark doodad something that we can get from LMDSS? There's actually, I mean, and no one here other than Lee and myself have. Oh, Stefan's been up there once, would be able to answer this. So I'll have to throw that out to the comments section, and any of the ASV members who have been to our dark sky site,
If-
the LMDSS.
What?
This
Mark.
is the Leon Mao dark sky site.
Mark, if you can get Centaurus, Carina Nebula, you'll be able to get it.
You'll be able to get it? Okay, well, there you go, Bill.
You just need a fast lens and a
Fast
dark
lens.
Yep.
All right, there we go. Yes, Bill, you can image the dark Doodad from the LMDSS. And for those who aren't ASV members, the LMDSS is the Leon Mao dark sky site, which is the ASV's dark sky site north of Heathcote, which we are currently in the process of putting wheelchair accessible pathways or all abilities pathways around and constructing an all abilities accessible telescope at. So to do what Kim's saying is to try and bring astronomy not just through live stacking, but also visually through a telescope to those who can't climb a ladder and stand up and get up and have a look through an eyepiece. Something that we're working on at the moment. Now,
just finally, that image that was on the screen, I think it's a 2-panel mosaic, and I think it was about 12 or 20 hours in total, but it was a very fast lens. But yeah, it can be done. I mean, it's not an impossible target.
It's a very, very impressive image.
Yeah.
I suppose the fact that it is dark means that there's a bit of processing goes on, more than likely, when it comes to having to sort of dull the stars and everything else to get that much dark, so to speak.
Yeah, well, I mean, I had where is it here? I had can't see that now. That was about 40 minutes, and that was from suburbia. And you've got much better conditions than a dark sky site. And you can start to make it out there. You just need a wide angle fast lens.
You can see that dark patch running through there. Almost looks like a Photoshop smudge, but it's not.
Yeah, you can make it out. It's just
you can even make it out there,
yeah.
You can even see it there on the right-hand side. So there you go, Bill.
By not seeing.
There you go, Bill. You'll be able to get that one from the dark sky site, which one of our viewers, Lalia, has wonderfully named the Love My Dark Sense of Satirical Humour. I think that's the LMDSS is what it's going to be called from now on. Love My Dark Sense of Satirical Humour. It's no longer the Leon Mao Dark Sky site. Now, the next object we're going to look at is the Running Chicken Nebula. So this is an image taken by Anne-Marie of the Running Chicken Nebula. And I know people say they can see the running chicken in this, but I can't see a chicken in this at all. I see the face of one of the characters from Beetlejuice. Woo, Anne-Marie, where
Sorry.
are you going?
Sorry.
Yeah, I see the face of one of the characters of from Beetlejuice in this when they stretch their nose out and in the blue area there. But that's me. That's my weird sense of humour. Now, Stefan, do you want to tell us a little bit about the Running Chicken Nebula? I know we'll jump over to Claire and Kim after that.
Sure. So this, in contrast to the Absorption Nebula that we just looked at, the Dark Doodad, this is an emission nebula, and actually a spectacularly bright one as well. It's a fantastic target to image. So the Running Chicken, IC 2944, is located in the constellation Centaurus, and it's located around 6,500 light years away. It's around 140 light years in diameter from end to end, so it is, again, quite a large nebula, and its magnitude around 4.5, or at least the open cluster within it is. So these emission nebula, these are usually new star-forming regions. So you can see, if you zoom into the center of the image, there's this sort of loose, open cluster of, again, young, big, hot blue stars that are emitting ultraviolet radiation. So you can see, towards the center, that sort of almost rectangular-looking collection of big blue stars. And they're responsible for illuminating the gas in their surroundings. And actually, if you look right in the middle of that collection of blue stars, you'll see this little sort of brown-looking thing. And that's not actually a stain on the sensor of the camera or anything like that. It's not dust. This is a real object within this nebula called a Bok globule, named after the astronomer Bart Bok, who I assume first described these. And so these are the sort of regions where the gas and dust has collapsed down to a high enough density that it's starting to block out some of the light behind them. So these Bok globules, these are what we think of as sort of really protoplanetary or proto-star systems. So when these globs sort of condense down under their own gravity even further, they'll eventually ignite in a nuclear reaction, giving birth to new stars.
So presumably then, if people can't, not everyone can actually see that it's a chicken, perhaps that's actually why they call it the running chicken, because of the Bok reference. Bok Bok.
I think what's also really interesting here, I never thought of that, Bok Bok, that's fantastic. Those black ones in that actual image in this particular nebulae, or Lambda Centauri, or IC2944, those black ones, those are black or brown, they are actually called Thackeray's globules. So those particular group, because we like to name everything, so that one's called Thackeray's globules. But what's really interesting about these particular Bok globules is, as Stefan said, normally we see star formation. They're associated with star formation because they are some of the coolest areas inside gas and dust that form the stars. So these are the coolest areas we know. But these particular Bok globules, we actually have never found any evidence that they are, in fact, have any star formation inside them. So I think that's really interesting. Just these ones alone, they seem to be a little bit different. Either that, or we just haven't found what we're looking for yet.
Can I ask why?
What do you mean why? Why we haven't found it?
Yeah. What makes these sort of Bok globules different in the fact that we don't see any star formation or evidence of that? Is there not enough material, or?
I don't think we really know. I think that's why they're a bit unusual, because even though they are clearly Bok globules, they're not doing what we expect them to do. And unfortunately, with astrophysics and astronomy, it really just comes down to finding more data for either updating our models or seeing new things. So I don't really know. And we also don't really know much about Bok globules, how they form, or the actual structure inside them. So without having that sort of, I guess, physics understanding of what's going on inside them, I can't really answer that. And it's definitely not my specialty, but yeah.
Oh, cool.
I always thought they were. Are they Bok globules? Are they only in the running chicken nebula? Bok, 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 bok.
See, that's the problem when you go away for a toilet break.
Oh, did I miss that joke? Did I?
I've done that joke already.
No, they're in lots of places. They're in other, for example, NGC 281. They're in other galaxies as well. They're just associated with the H2 regions, which we talked about before, being those sort of star formation regions. Bok globules are, in fact, in other places, so they're not just in the running chicken.
I was trying to be dad jokey, and it's just failed, hasn't it?
Did I cut your head off and leave you running around like a headless chook? Or?
Oh my God, I've seen that happen as a kid, and probably. Yeah. Now I'm going to jump with it.
Just to help people, visualize it a little bit better.
No, I disagree completely. And I can see Kim shaking his head as well. So I think I will jump across to Kim's image.
Yep.
Running chicken nebula. So I can get Kim to have a chat to us about this one.
Let me give you the real running chicken.
Running chicken, yes. Is it a butterfly chicken? You know, when they butterfly a chicken and fry it? Is that what it is?
No. It's a different view, I guess. So where it is in the sky, it's at the bottom of the Southern Cross and to the right a little bit, right? So it's between Eta Carinae Nebula and the bottom star, Alpha Crucis, roughly midway. That's where it's located, for all of you who want to go and find the running chicken. And it's quite easy to image. This is an image, I don't have the details in front of me here, but it's taken from a dark sky site with a narrow band filter. Again, you can see the Bok globules there. And yeah, they are actually associated, as was mentioned earlier, with the actual nebula itself. They're not foreground objects. And you can tell that from the detail around them as well. They actually are interacting. The way I see it is I actually see the Chook's head up in the top right corner there. And I kind of see it that way. And that's the head. There's a sort of... anyhow, I also refer to it as the Roadkill Nebula because I reckon I can see tyre tracks right through the middle of it. So hopefully that's not too gruesome for some people. But that's how I see it. Now, Paul Hazy took an image of it as well, and I've superimposed that on top of this one. And that's his. And he's actually used narrow band as well, but he's actually brought out the colours differently, perhaps a little like one of the earlier images that was presented. And yeah, that's his image there, and you can see the colours from probably the oxygen 3, I imagine, coming through there. Anyhow, that's Paul's image, and that was my image earlier. So yeah, the running chicken.
Now
you know where it is in the sky too.
Yeah, and I just want you to know that according to Adam, all these chicken jokes are foul.
Exactly.
Yeah, and Gerald, who should be asleep because he's got work at 4 a.m. in the morning, Gerald, go to sleep, says he sees a smiling pig. So I will, when Gerald's back on our next stream, we'll get Gerald to explain to us how he sees this smiling pig. That's a good one.
I kind of see that actually.
Yeah, I'm curious to see what he thinks about that. Why he thinks it's a smiling pig. Marina wants to know: will this session be on YouTube at all? Yes, Marina. This is being streamed to YouTube as well, to the ASV's YouTube and the ASSA's YouTube as well. And the Chook's head is very attractive. They are when they're still on the Chook. We've got Sandy, these images. The images and info are incredible. I feel like I need Marvin the Martian spaceship to dart among the clusters. I'm not sure Marvin's spaceship would be fast enough, actually. I reckon we might need something like a Millennium Falcon or something like that. So the next image that's on our list is Eta Carinae.
Ooh. Do you want me to talk to that as well?
Yeah, if you've got it ready to go while the others get their images ready.
Yeah. I've got it here. Then I've got a couple of slides, and then I'll just
chuck yours on. We'll have a chat about yours, and then we'll get the others to.
All right. So we can see that okay. Hopefully, just put it back up. Sorry. This basically shows its location again from the Southern Cross. Go past the running chicken, about the same amount, and there's Eta Carinae, which is quite a bright object. You can see it quite easily in binoculars. Yeah, there's an image I took. That's quite a number of exposures, 66 odd, taken from a suburban location with a narrow band filter. And this was taken with a full moon in the sky as well, from a really heavily light polluted location. So it's amazing what you can do with narrow band filters in suburbia, with a very small scope as well, and not a particularly fast scope either. So that's with Paul's image superimposed over the top. As well, and that was taken with a larger scope, or maybe not a larger scope, a better scope, I think. Might be in Takahashi. Fortunately, he's offline. So yeah, that's Paul's image. I don't know that I've got more than that. No, I don't have anything more on that one. That's all I have. So that's Paul's. That was mine, and I was pretty happy with that one. Although I reckon I can do better in the future. Yeah. So that's all I've got. Someone might want to talk to that.
I'll throw that open to Stefan and Claire, whoever wants to jump in first.
Well, actually, would you mind sharing my screen, Mark?
No. Yes, I will share your screen.
Cheers. Can you see the nebula?
Yes, we can.
Yeah, so comparing to the image that we just saw from Paul, so Paul's image was in what we call RGB, or true color. Whereas this image that I've taken, this is what we call a color mapped image. So for this image, I didn't take this photo through red, green, and blue filters. I took it through narrowband filters, hydrogen alpha, sulfur 2, and oxygen 3. And then I mapped those to what we call the Hubble palette. So something that the Hubble telescope also maps. But and so that sort of gives you a sort of different color. So this isn't exactly how our eyes would see the color, but it is still a representation of the data that we do get. But one thing that I just wanted to point out is in this greater Carinae Nebula, there's this one really fantastic star called Eta Carinae, which is actually down here next to the Keyhole Nebula. And if you can see, right in the center of the image is the star Eta Carinae. And you might be able to tell that it's not quite like the rest of the stars in the image. It's not a point source. Eta Carinae is surrounded by a larger sort of, or a large outgassing called the Homunculus Nebula. And you can see it sort of surrounding that yellow star in the middle, Eta Carinae. It sort of looks like a peanut. It's what we call a bipolar nebula. And that's because this star, Eta Carinae, is a really incredibly massive star. And in the 1800s, I believe it was, it underwent something called the Great Eruption, where it wanted to go supernova, but it didn't. It sort of burnt. It let out this large outgassing, this eruption, and became much, much brighter. And what you see there, that peanut shape, is the Homunculus Nebula. And if I just go over to my slides here, I've got an image of that taken by Hubble. So I'll just move that boring stuff. So there you go. That's the Homunculus Nebula, an image taken by Hubble. So this is the star Eta Carinae in the center. This really massive star that's actually a binary system. Yeah.
Do you have anything to add to that, Claire?
Well, so homunculus means little man, and to me it looks more like two lobes of a brain. And then inside, if you go deeper than that, there's actually an even smaller structure in there called the baby homunculus. So it's a baby little man. So there's actually a picture captured, I think, I'm guessing it's in the infrared even further, which you can go and have a look on in Hubble. And it's basically all the stellar material blown off that inner star system. But what I thought I'd quickly mention is, because everyone was so interested in Bok globules, is that there's actually a Bok globule, and I'm sorry to be rude here, inside the Keyhole Nebula, which is in this sort of bigger nebula. And if you don't mind, I'm going to share my screen, and I'm going to tell you what it's called.
I don't know if I'll allow that.
No?
No, I will. I will. Go for it. Share away.
All right.
I'm going to share my screen after you've finished as well, before we move to the next subject, so it's all good.
I have to just, how do I allow system preferences? No, but you need to see it. It's fantastic.
You have to have the share plus. You've got to click the share plus.
And I've got to go through all my system preferences. Oh, you can take over my computer.
Technology, it wants to
it
stalk
won't let
you.
me. All right, I'm going to let everybody else at home go and Google this, or use your chosen web browsing service to find out this. It's called the Defiant Finger. And I'd like
Oh, you've told me about this.
It's called the Defiant Finger. It's in the Keyhole Nebula. I am more than happy for somebody to go and find it. Otherwise, I have to restart all my Chrome, and that means I have to leave you all. So I don't want to do that. So please look up the Defiant Finger. It's inside the Keyhole Nebula, which is inside the Carinae Nebula. And that is all I'm going to say about that.
All right, I'm trying. What we're going to do quickly. Let's go across to Andy's got an image of the Eta Carinae. Now, while we're doing that, we have a question, and I think this might be one for you, Claire. Neil, who's a very active ASV and MBO member, has also helped us on live streams as well, wants to know, is it only UV frequency light that causes atoms to become excited and eventually emit light?
So I think that's a really good question, and I hope you don't mind. I'm going to take you back to a little bit of chemistry. And even though quasars is my thing, Shannon, there's some things you should never Google. Correct. Let's not list them today. So I'm going to take you back to a little bit of chemistry, which is super fun. Got a nucleus, right, which is the protons and the neutrons inside. So inside an atom, right, the smallest sort of division that is still the same of the material. So a hydrogen atom, for example, is just a proton, and it's got an electron sort of orbiting it. It kind of exists around it in an energy level shell. And that energy level shell is basically defined by its ability to move around and be attracted to that positive. So the electron's negative and the proton's positive. So that kind of sits in this shell where its energy is perfect to sit that far away. And when light of a certain, so there are some spare energy shells above that electron, right? So it can only go into these particular shells. It can't just kind of like be in sort of 2.5. It has to basically go up a story, like lifts in an elevator. You can't kind of, so like lifts in a multi-story building. You can't kind of stop at 2.5. And I'm kind of grateful for that. I've seen pictures of people trying to get out of a lift at 2.5. It's not for me. So electrons, if they want to go to a higher level, they have to go fully to the higher level. So they need to get that energy from somewhere. And what happens is that incoming light will hit these atoms that are sitting there with an electron on them, and they will jump up to the next energy level if it's the right size. It has to be the perfect wavelength. And it goes, oh, thank you, I'll take that. It jumps up there. But just like human beings, so that bottom level is what I call the couch level. It's where we all want to be, sitting with some chips and the TV, watching in our most comfortable state. That's the ground level. And then you might get a little pinprick and be like, whoop, and you jump up and you get into that sort of next energy level. And you have to, the incoming light has to be exactly that energy. When that electron doesn't really like staying up there, like I don't want to stay standing forever. So eventually I'm going to give up that energy, the exact same amount of energy. I'm going to blow it off, and then I'm going to sit back on the couch into my ground state. So it's actually that second process of the electron coming down a level that emits the light, and the color of the light, the wavelength of the light corresponds exactly to that amount of energy. If you give it lots of energy in the first place, it's going to jump up a lot of levels. Sometimes it comes all the way down back to the ground state. Sometimes it sort of stops off at like the pub and then stops off at the neighbor's house and then eventually gets back to the couch. So sometimes there are a bunch of different light colors that are released on its way back to the ground state. So that's one way that light can be produced with electrons and atoms. So when the light comes in and hits it and an electron comes down. The other way is something called photoionization, which is actually what I specialize in. And that is where electrons are completely blown off. Way too much energy. The proton can't even hold the electron anymore. It leaves the atom completely. And then when it cools down a bit, the electron kind of goes, hey, look, I'm sorry about our fight. I want to come back. And then it actually gives off the energy so that it can actually still be attracted, and then will cascade down back to the couch or the ground state. The couch state is not the chemical name. Nobody else calls it that, just me. So the couch state, and that's where the light comes from. So to answer your question, Neil, those energy levels are different for every single element. There are basically an infinite number of them. So it doesn't have to be just UV light, absolutely. But UV light is typically what these stars give off. And so that's the light we sort of typically associate with these processes.
Thank you very much for a very detailed explanation. Some of that made sense. Some of it worried me. I'm not sure why they're going to the bar and then to their neighbours before they get home to the couch. That's a little bit concerning, that one.
And the rest of it took you back to high school.
Oh, I know. Yeah. Now, what we've got here is this is Space Engine, and Lee has got Space Engine zoomed in, Claire, on that little binary inside the, as I like to call it, the Hermocles, going back to my Simpsons days. And this is a nice close-up image of that little binary system that that was being spoken about before. So, Lee, if you'd like to maybe zoom out a bit and just show everybody exactly where that is. And while we're doing that, Claire, Neil says, thank you for the answer. If I see an electron at a pub, I'll tell them they look luminous, but they need to go home.
I feel like I've been given that advice before.
I'm sure quite a lot of us have been given that advice before. So there, you can see that little binary inside the homunculus. And there we go. There's another one. Thanks, Claire, for this explanation. Love the couch theory. Couch theory. It's a new theory, Claire. You've created. You've got to run with that now. Couch theory.
Woo!
Now, all of these lovely images, like Anne-Marie's image of Eta Carinae, These are all taken with some pretty impressive pieces of equipment. But I've noticed some people like Maritain. I'm technologically challenged and I live in the mid-north of SA. I love looking up at the night sky. Would I be better off with a set of binoculars to start off with? I can't afford much. Binoculars is a great place to start if you can't afford a telescope. That's for sure. Does anybody else have anything to add to that? You're all very silent.
I guess I can say, look, there are two major types of astronomy when you come into the hobby. There is visual, which is just looking through the telescope, looking through binoculars, and then photography, astrophotography. Astrophotography is quite technically challenging. There's a big learning curve when you come into it, but visual, anyone can do it. You can pick up a set of binoculars, you can pick up, set up your telescope. So if you have no experience, absolutely, visual is the way to start, and a pair of binoculars is, the lowest barrier to entry there is. Even if you're interested in taking photos, I think, a pair of binoculars, you can't go wrong. Learn your way around the night sky, learn some of the targets, some of the different target types. That's honestly the best way to start.
Now, Stefan, you've upset a couple of people. There are 3 types of astronomy. There's the dirty cousin, radio astronomy, that nobody likes to talk about, but everybody loves. There's actually a 4th, and one of our viewers has commented on it, and a smartphone. And this is my sort of area. I'm somewhere in between a visual astronomer and an astrophotographer. I don't have the fancy gear that astrophotographers have, but I do have a second-hand go-to telescope with a nice eyepiece. It's not worth thousands of dollars, that's for sure. But Stefan's right, you don't need to invest a great deal of dollars up front to work out what you like to do. Binoculars is a good start. If you can invest more and you can get a small go-to telescope, if you've got maybe like $1,000, $1,500, you might be able to pick up something decent enough. I've got a little 8-inch Meade, and what I'm about to share with you is an image I took using my phone up at our dark sky site. If I can Chrome tab, here we go, of Eta Carinae. That is using a phone of Eta Carinae. You can see the homunculus up in the top here, and that is what have we got? 33 20-second images using a phone attached to a tracking telescope that it's not worth a great deal of money. We call it the coffee grinder because it's so loud when it moves from one spot to another. And it shows that even with a phone, you can do some pretty impressive stuff when it comes to astronomy. That's for sure.
Even when you're talking, Mark, about the, you mentioned sort of $1,000 or something, which I think was, the Meade, which included the mount. I've got.
It was a little bit more than 1,000, but it wasn't.
But
massive amounts of dollars.
Even we do have an expensive scope, but also I've got one that I fixed up a little bit, which was one we bought over 20 years ago now. It was a 5-inch Newtonian. I think back then we probably paid, maybe $900 or something for it, because it was just I think we got it from National Geographic, so they overcharge a bit on the things like that. I've seen them in on eBay and Facebook Marketplace for $50, $100. So they're very easy, and most of these things were built quite well back then. It was usually the eyepieces that weren't the best, but the mirrors were pretty good, and they would well suit having a mobile phone with an attachment on them. Just to get a few, they're not go-tos, but you can probably get a cheap go-to, which is the electronic mount to follow. But yeah, it's it is pretty easy, but still, binoculars. What do you pay for those these days? About $50, $100.
Oh yeah, anywhere from $50 to a couple of $100, depending upon what you're getting and where you're getting them from.
Yeah.
So there we go. Dave Fisher has had a $99 LD 3-inch with a mod mount and a motor. If it works, if it holds the object in the sky and you can have a look at it and you can stick your phone up to it and take a photo, great. That's exactly, you know. And this image, what we're looking at here, this is Andy's setup. Please ignore the splatters of blood inside his tent there. That's from our Halloween special last year. He hasn't cleaned it off. So Andy's going to tell you exactly how much his telescope setup didn't cost.
Okay, now this was a $200 secondhand. $200 secondhand Newtonian. I bought on Ice and Space, and then I bought a secondhand. It's a 12-year-old DSLR. That was $230. And I've actually just bought one the other day, and it was $23 and actually worked too. So now this is probably, I'm getting up here, $230, I think it was, and this is second. This is my guide camera. But a lot of my images have been just taken with the scope, the DSLR. This is before I bought that, but this mount, I paid $700 for this mount, and it's a secondhand. It's an HEQ5. So really, my basic equipment, it's about $1,000, but just it's the mount really. Even just my DSLR on a tripod, I can take sort of 15-second images before I start to get star trails. But the Newtonian, I'd be lucky to do not even a second. So the mount is vital. And you can get cheaper mounts, like it's a Skywatcher star trackers and things like that. They're mainly for DSLRs, but it's the mount which gets you the time. You know, you need to get above 30 seconds to 60 seconds. That's a sort of bare minimum. But once if you get it higher than that, then you'll start to need a guide camera like this. All this is secondhand. That's the beauty about this stuff. I bought it all secondhand, except for my tent. I paid new for that.
The tent with blood on it. So yeah, I'm not sure whether anyone believes me when I said that was actually from our Halloween special last year, or whether you've just killed somebody in the tent.
That's right.
Just live in the country.
I'm out in the middle of nowhere, right? There's not many people around here, so it's very dark at night. I invite people here all the time.
Now,
come to a dark sky and look at the night sky with me. Drive down a dirt road in the middle of nowhere.
I'm not going to travel down a dirt road out in the middle of the nowhere to look at a dark sky site with a man who has a tent with fake blood in it. The next object we're going to look at is Proxima Centauri, and I'm going to jump across to Kim. Take it away, Kim. Run us through Proxima Centauri, if you will.
Actually, just before I do that, if you just take that slide off.
Now,
this getting back on the conversation about, this is expensive gear. One thing we purchased for the Society and its members about a year ago was a Takahashi scope that came up from an estate. And we're actually outfitting it, and I've got it here because we're working on it, with a nice camera and a focuser. See an automatic focus at the bottom there. Yep. And we've got an ASI Air for it as well. But this is a 90mm Sky 90 Takahashi, which is a lovely scope if you've ever looked through one. But we're going to make it available to our members on short-term loan, so they can actually play around with this tech at home or wherever they want. And hopefully we get it back.
in one piece as well.
In one piece would be ideal, but we'll take it in multiple pieces if necessary. Okay, so I'll go and put another image here. All right, so back to this sky map, and down the bottom left there, you can see I've got a green square labeled Proxima Centauri. Now, the bright star next to it is Alpha Centauri, and it's actually a triple star system. So if you look through its telescope, it's actually you'll see two very similar stars very close to each other. But there's actually a third star which is some distance away, and that star is called Proxima Centauri. And it's located at the centre of that square I've got on the screen there. And it's actually very faint. It's magnitude 11, which makes it well beyond binocular sort of view as well. And most people have not seen it. The important thing about Proxima is actually out of the triple star system, it's actually the closest star to our sun. So I thought I'd turn my telescope to it and just dialed in the coordinates and took a few images. And there it is in the middle of that shot. These are a number of 30-second exposures taken from my backyard. And there it was. I'd never seen this object before. And it's quite a significant object from in terms of our neighbourhood and where we are in our part of the galaxy. This is the closest star to us, and it's a red dwarf. And I'm sure either Claire or others will describe what a red dwarf is. But I will say most of the stars in our galaxy are red dwarfs. They're very faint. None are visible to the naked eye. I think out of the closest 50 stars, 40 of them are red dwarfs, closest stars to our sun. 40 of them are red dwarfs. Now, we know there are planets orbiting this star, which is very exciting, closest star to ours, but there's some bad news. This is a flare star. It erupts and puts out very intense levels of radiation, ultraviolet radiation, that bathe the planets in extreme levels of radiation, suggesting life may not actually be possible on the planets orbiting the star. One of which happens to be in the so-called Goldilocks or habitable zone, where liquid water could actually be present on its surface. So anyhow, I thought I'd share that image. It's something that most people do not regularly see, even through a telescope visually. It's actually quite hard to find. So, but as an image, you can dial it up, and there it is. And again, this was done from suburbia with a number of 30-second shots, just to bring out to reduce the noise. Yeah, there you go.
Now, Lee has jumped into Proxima Centauri on Space Engine. It's gone right in there. Now,
So, yeah,
I
right.
don't know. I think Stefan's back as well. So, Claire, Stefan, take it away.
Well, I actually just want to comment on these flares. Within this flare information, these signals, there's a whole bunch of this decade. There's a whole lot of money put towards sort of the SETI, not just SETI, but there's other projects, and one of them is called Breakthrough Listen. And somebody mentioned before about the signal from extraterrestrial life. I say extraterrestrial life with caution because, I mean, obviously it's binary. It's either there or it's not. But basically, Breakthrough Listen is sort of computational software, and it goes through current signals that we get from other observatories, in this case, Parkes. So Parkes has a whole bunch of emission. Parkes was listening to this star essentially in looking for radio emission, and this Breakthrough Listen project ran the software through it and actually found faint signals in a narrowband transmission frequency of about 982.002 megahertz. Which is rarely used by human-made transmitters, which means that it's probably not contamination from Earth. And so this signal showed up during 5 30-minute periods over several days. But when the telescope was turned away from the star, the signal vanished. So it sort of seemed to be very constrained to that particular star. It doesn't mean that it's coming from anything ET like, but it certainly is just an interesting signal within the data. And so that's what I think, one of the things that somebody might have been trying to mention before about a signal that we found, it was actually this star, this flare star, but it was a specific frequency within the radio flare data coming from Parkes.
And I guess one thing I can, I think one thing I can add. So we're talking about receiving signals from extraterrestrials, but, to an extraterrestrial species, we would be extraterrestrials to them. And in fact, we have sent our own signals towards Proxima Centauri, a physical signal in the form of a golden record on board Voyager 1. So the Voyager spacecraft, these were probes that were sent off in the 70s and essentially sent off out outside of our own solar system out into interstellar space. And Voyager 1, the first of these spacecraft, was sent off in the direction of Proxima Centauri. And on board this spacecraft, there's a golden record, a record made of solid gold, on which is recorded a number of recordings of, humanity's, essentially our first words out into the cosmos. And you can actually look this up on YouTube, and you can listen to what was recorded on these golden records. It's it's quite beautiful, I think.
I also thought I might comment quickly. Oh, they're the records. They're really cool.
There we go.
I'm not sure what I'd do.
I think there's some Pink Floyd on there, isn't there? Maybe some Led Zeppelin.
I hope there's Led Zeppelin. I'd agree with that.
Has to be some Led Zeppelin on there. If there's not, I'll be disappointed.
I thought I'd just comment quickly on red dwarfs. So before we were talking about O's and B's being the brightest, biggest, most sort of hot stars. If you think about it, OB are fine, girl or guy, kiss me. M is last. And so those are the red dwarf classifications. They're sort of at the bottom. They're the reddest because they're the least high temperature, so they've got the lowest temperature of the stars. So we're talking about surface temperatures of about 2,500 to around 4,000, so quite a lot less than a surface of our sun, 5,000. And they have much smaller masses, so just about a tenth to a half of the mass of our sun, and their actual sizes are sort of like a tenth to sort of 3/10 or so of the diameter of our sun. So they're absolutely tiny, and it's actually funnily enough, they're really, really common because they're so tiny. They don't need very much gas to sort of get going. And if you think about what I was talking about before, where it's a fine balance between making a star and then blowing off all the material and doing that in time. So basically gathering enough material to make the star before the star ignites to blow away the material. These are kind of that limit. And what's interesting about these stars, just as a final point, basically is that when you think about the sun, we have a bunch of hydrogen in the sun. It's making helium in the core, and then eventually that helium will then fuse as well, and then off we go into this red giant puffy phase. But red dwarfs actually don't do that because they actually have mixing. So they have what's called convection, which is a physics process where essentially hot stuff expands and rises, and then as it cools, it contracts and sinks. So red dwarfs are fully convective, which means that the whole interior of this star actually churns around, which doesn't happen in stars like our sun. So this star, this red dwarf, will live a very, very long life, but it will never become one of these massive red giants, and it won't do the planetary nebula thing. So I'm pretty happy for it because its little flares are probably its most exciting thing that it's going to have for most of its life.
It's got a lot of pretend sunspots on there too through Space Engine. A lot of little pretend fake spots on there. Now, next,
it's probably got magnetism in there as well. I mean,
it probably has.
Yeah.
Now, I'm not sure who is putting red on our little spreadsheet in the background here, but thank you. The next object is the Eagle Nebula. So if our oh, hey, we've got one ready to rock of the Eagle Nebula from Andy. So, Andy, can you tell us a little bit about this image that you've taken of the Eagle Nebula? Now, I know it's the Eagle Nebula, and I know it's meant to look like an eagle, but the bit at the top that's the eagle's head kind of looks like the top of a coat hanger.
Yeah, that's
I
right.
like to call it the coat hanger nebula.
The coat hanger, yeah.
My grandmother would be horrified because this one has some very special meaning to me and my grandmother and my mother. But tell us about this image.
Okay, this is done in hydrogen alpha. So what I do, I've got a little filter, a hydrogen alpha filter. I put that on my DSLR and hook it in. And this was about 3 hours altogether. It was, they were 5-minute exposures. I've got a few others. And in here is the classic Hubble pillars of creation. I've got a couple of others. Actually, that's not a good one. That's zoomed in. This is an RGB version of it, which is just a straight DSLR. And because my DSLR has been modded, it's had the infrared filter taken off, and that's why it's got a red cast to it, and that's why it can let hydrogen alpha in. Here's another one. I like the black and white images, which they seem to show it a bit better. But same thing. This is the pillars of creation, which I've sort of zoomed in on this with my camera. But yeah, it's a good object. It's quite easy to find, yeah, I get a bit blown out with my stars because of the Newtonian. That's what you tend to get. It's nowhere near as sharp as the reflectors. The refractors. Me using a reflector, but I reckon there should be some stunning images coming up in a minute from someone else. So I'll pass it on.
Let's jump across to Lee's.
Well, that's actually not mine. That's Blake's.
Oh, that is Blake's. Okay, so long story short, Blake, my son, took some images through eye telescope of Eagle Nebula, and Lee helped him process it and turn it into colour. And this will be a bit emotional. This actually was put on my grandmother's coffin earlier this year. So it's a bit of an emotional one, this one for me. But yeah, so Lee, thank you very much for processing that. But this is actually my 14-year-old son's image of Eagle Nebula that Lee helped him put into colour. Do you remember the details of this image, Lee, by any chance?
I'd have to open them up in the in DSS.
I can't remember them. It was a pretty hazy time.
Yeah, like I mean, if you look at the original sort of the mono shots of each, so that was hydrogen alpha. Yep. Then that was oxygen, and then this here is hang on. UHC.
I can't believe you've still got this data still hanging around. It's quite impressive.
I think this is the thing about a significant number of astrophotographers is we keep all the data.
Even if it's not your own.
Even if it's not our own. I mean, yeah, it's just you store it on hard drives, and I think actually the name of the files I'm sure someone else has got an image. I'll see if I can find the length of the exposure on those.
All right, before you do that, just so that everyone knows, iTelescope is a remote telescope program, basically it's up at Siding Springs Observatory in New South Wales near Coonabarabran, and you can literally pay time to hook onto their telescopes to take images. So if you want to get into astrophotography, if you want to learn how to do it, you can use their equipment and you can take images and you can learn to process those images. They have lots of different telescopes that you can pay for time on, different field of views, different types of telescopes. It's an amazing little system, and it's well worth exploring if you're very keen on learning astrophotography and don't want to shell out the dollars for the equipment straight up. It's a cost-effective way to see if you are truly interested in it. But what we'll do while Lee works out what the exposure links on those images were, we'll jump across to Anne-Marie's version of it, which is quite impressive, Anne-Marie. How many hours is this one?
4.5 hours.
Oh, come on. Last weekend you were sharing images that were 9 and 12 hours worth of data.
I know. Yeah, just 4.5. They're 4-minute exposures, and that's in the hydrogen alpha O3 and S2 in the Hubble palette, processed in Hubble palette.
It's beautiful, absolutely beautiful, and you can actually see the eagle in this, and the pillars of creation is
pillars, yeah,
quite distinct in this image as well.
Yeah, I'm still working on it.
While we're zoomed in on the pillars, I'll jump across to Stefan, Claire, whoever wants to jump in. I'm waiting to see who's going to unmute first. Stefan did. Tell us a little bit about pillars of creation.
Sure. Well, I guess what I'll say is in this image, these pillars kind of look small. They look almost like your fingers. But the largest pillar, the one on the left, is around 4 light years long. compared to some of the distances we've been talking about, millions of light years, that may not sound like a lot, but 4 light years is an incredible distance still. If we were to hop on the fastest man-made object, the Parker Solar Probe, it would take us almost 7,000 years to traverse the length of one of these pillars. So they may not look like it, but are enormous objects. And we're actually quite lucky that we get to see them, because these pillars are being eroded by the big high-energy stars surrounding them. And it's estimated that within the next 100,000 or so years, they'll be completely eroded away. So, yeah, I think we're quite lucky that we get to see these beautiful objects. And the photo that we see in front of us, this is in the visible spectrum of light. But when we train other telescopes to look at these objects, in particular infrared telescopes like the upcoming James Webb Space Telescope will be, we can see through these dense clouds, and we can see right into the middle of them where some of the star formation is occurring.
Don't jinx the James Webb Telescope.
Yeah, it's definitely going to launch this year, 100%.
Don't jinx it.
Right.
It was meant to launch 13 years ago. Don't jinx it.
I've actually got a friend that works on JWST, so there you go. The only thing I was going to say was that I've got a friend who works on James Webb, so she does a lot of she's sort of an astrophysicist. She works on James Webb.
Can we blame her then for the 13 years away?
I don't think so, no. But I don't think you can jinx it anymore, right?
No, you can't jinx it anymore.
I was actually just
already an unlucky number.
I was just going to add to that before, when we talk about palettes, I'm assuming when you talk about Hubble palette, it's about assigning the visual colors we see with our eyeballs in a photograph to the wavelengths in the filters. And so in the Hubble palette, and in this one as well, we can actually see sort of blues are oxygens and reds are sulfurs. So sulfur, the element, and green has so a bit of nitrogen and hydrogen. So they're different energy transitions for hydrogen than the red that we saw earlier. So yeah, so we've got green, reds, and blues in there, and they all mix together, and they make this absolutely stunning. Probably one of my favorite as well, nebulae to look at. That's all.
Now, it's like, sorry, Eagle Nebula, as I said, it's like it holds a very dear place in my heart. So I thank everybody for sharing their images of Eagle Nebula. Andy, what have you got there of Eagle Nebula? Which one is this?
Whoa.
No, it's not mine. It's a Hubble.
I know it's not yours. Your equipment's not that good.
No, it's in infrared, right? This is the infrared version of the pillars. So you can just. It's pretty well. It's the most stunning image I've seen. Some people blend this one because the good thing about the NASA data, it's downloadable. You can download everything which NASA take photo images of. You can download and mess with it yourself. Some of it's in pretty tricky format, but a lot of it's in FITS format. And there's repositories where you can download all this stuff, but this one is just the NASA release, and that's the good thing about NASA. At least their data's free. Once they finish with it, they release it out. Except the stuff they don't want you to see. No, there's nothing like that.
Conspiracy theory.
We won't get the conspiracy people talking. No, conspiracy theory. There's nothing like that. It's just,
All right. Now, we're going to jump across to a very, very interesting object, and one close to Kim's heart this time, and for good reason. We're going to have a look at the Gum Nebula, and I will say, for those astrophotographers that haven't imaged this nebula, and for those of you who have never heard of the Gum Nebula, Kim's going to explain a little bit about it and how important it is to Australian astronomy.
Thank you, Mark. Okay, again, I have a map here of the night sky showing the Southern Cross on the left and the pointers. And we've already been past the running chicken, and we've covered the keyhole nebula, the Eta Carinae Nebula. If we keep moving in that direction, we come to this very large object indicated by this green oval called the Gum Nebula. This is not easily seen. It's actually not even easily photographed because it actually spans about 36 degrees of the sky. And I believe it's the single largest object in the sky. And it's actually named after an Australian astronomer. And this is an image of it taken by one of our members, Jerry. And I just texted Jerry a moment ago, and he was going to tell me how many hours he spent on this. And he says 3 hours each. Okay, so let me get into it. So that's an image taken by Jerry Velatus of the Gum Nebula, taken very recently. And I've superimposed it and aligned the stars with the map that's in the background there. And you'll see it is actually quite a large object. If you compare it to Eta Carinae Nebula, which is on the left here, it's actually much, much larger than that. So it spans about 36 degrees. It's a supernova remnant, believed to be a supernova remnant from an explosion, a star that exploded about a million years ago is what I've read. This is a better image of it. This is the same image taken by Jerry. He says he spent about 3 hours each of hydrogen alpha and oxygen 3 on this, using a 35mm Pentax lens on a dedicated digital astro camera from suburban Adelaide using narrowband filters, which is quite amazing if you ask me. Lovely image. Supernova remnant. There's actually another remnant in there as well. It's the Vela supernova remnant, which is that greenish, bluish, much smaller remnant on the left-hand side of that bigger red image. So the big red nebula, that's the Gum Nebula, and the smaller one, which is in green, is the Vela supernova remnant, which most people, I think, are familiar with. Anyhow, that's the Gum Nebula, and I'm sure others may want to talk a little bit about it. But I also wanted to cover a few things about its history, and I'll cover that first, and I'll come back to this, if that's okay. So, who discovered the Gum Nebula? Well, as I said, it's an Australian, a guy called Colin Stanley Gum, who was born in 1924, but didn't live that very long at all. Born in South Australia, back in 24, only child of Ivy, and his father had already passed away by the time he was born. So there's a bit of tragedy there already. Very smart kid, dux of Gladstone High School, which was up in the Southern Flinders Ranges. That was in the first year at school. Got a scholarship to go to Prince Alfred College, which is one of the premier private colleges in Adelaide. Got his honours degree in Bachelor of Science in Physics at Adelaide University. Quickly went on and got a Master of Science degree from Adelaide for work he'd done previously at Mount Stromlo Observatory. And was actually the person who got his first ever PhD in astronomy from the Australian National University. So quite an achiever, and his thesis was on a study of diffuse southern hydrogen alpha nebulae. Namely, what's become known as the Gum Nebula. So he went looking for that and found it. And back in the day, guess what? They didn't have Photoshop. They didn't have all these digital tools we have these days. And he came up with very innovative methods for actually identifying images of H alpha in the sky and combining them and subtracting other visual imagery from those images to actually bring out the H alpha regions. He was appointed as a research fellow in 56, shortly after his PhD, to CSIRO, and did radio physics for a while. And in 59, he got into optical astronomy. He was appointed there. And numerous scientific achievements in his short career. The big one was the search and discovery of the H alpha regions in the southern Milky Way, and in particular the Gum Nebula, which bears his name. And he's also honoured not only in the sky, but also on the moon. He's one of the only 4 Australians who has a crater named after him on the moon. Now, admittedly, it is at longitude, I think 88.6 degrees. So it's right on the edge, and you need the moon to be having librated in the right sort of degrees to actually see the crater from Earth, at least. But this guy died tragically at a very young age. He was in Europe, and he died in a skiing accident in Switzerland. I first learnt about him. I stumbled upon his resting place, quite accidentally, I might add. and there's a sundial, which I also have an interest in, and it's dedicated to Colin. It's a pretty ordinary sundial. It's actually, we found out it's actually designed for Sydney. It's ornamental only. It's mass produced.
Everything's about Sydney, isn't it?
Apparently. But there is a plaque there in the cemetery, which is just down the road from where I live.
Was that too much of a burn too early?
Who knows?
Who knows?
Who knows? But anyhow, I thought, well, hang on, here's this guy, very high achiever, honoured in the sky, honoured on the moon. And as far as I know, there's nothing apart from this bird poop-covered sundial that's vandalised, by the way, honouring him on Earth. So I thought, well, his 100 years is coming up in terms of his birth. About 3 years from now, and I thought, well, maybe we should do something to come up with a better memorial for this chap. So I started making some inquiries, and that's basically his story, which I don't think is actually well known in Australia at all. Very, very high achiever. All right, so there you go. That's Colin, and that's the going back a slide, the Gum Nebula.
Now, I think. A fundraising setup that you and I were talking about earlier today for him is a great idea, and I think it's something that everyone should be able to get behind. As you said, this is a guy who, an Australian astronomer who's discovered a nebula that most people haven't heard about, and now, 100 years on, we should do something about that. And so you've got my support, Kim. I'm happy to put something towards.
Well, as I said, he's
what you might want to do with this, and I'm happy to help promote getting something done for this, because this is an important piece of Australian astronomy.
Now, there may be some memorial to him already. I've not found that, but it's worth inquiring and taking it a bit further, given his 100 years of his birth is coming up.
Yeah. Absolutely. And added to that, we've now got a challenge for our moon viewing nights to try and find. So what was it? Is it a crater?
Yeah, it's a crater. It's in the southeast corner. So it's but when I say corner, like I said, 88.6 degrees, and we've got 90 degrees in longitude, so it's absolutely on the edge.
Right on the edge.
It really is an observing challenge.
It's there. So the challenge for our next full moon or for our next lunar stream is we're going to try and find this crater. I think it's a great idea. It's something really interesting to do. In fact, we might try and put the details out to the public about where that crater is and see if anybody out there can image that crater on the moon when it's in the right position, because it would be good to see, good to promote an Australian astronomer who's got a crater named after him.
There are four Australians have craters named after them, but this
only 4. That's what I mean. So there's only 4. He's one of 4.
Yep.
So who are the other 3? Just out of curiosity.
You'll have to Google that. I
think I'll put you on the spot too much there.
Yeah, it's hard work. I was going to include it. I ran out of time. In fact, I was typing the slide as you guys were speaking.
No, all good. Now, I think Stefan's got something to add to this with the Gum Nebula. Stefan,
yeah.
Floor is
So
yours.
if you leave the screen up as it is just for a second, so here you can see the whole extent of the Gum Nebula, and looking at it, you may compare it to some of the other nebulae that you've seen, some of the other photos, and you may think that when you look up in the night sky, it might just be a tiny thing, but really, this entire Gum Nebula is around 80. I think it was something like 80 degrees wide in the night sky. Absolutely enormous. 80 times the diameter of the moon in the night sky. So this is a really, really large object, but it's just incredibly, incredibly dim. So it's not something that you'll be able to see with your eyes, and binoculars won't even help you because it's actually a really, really large object. But if we go back to the full photo of it, this is actually an astrophotographer's dream, because within this huge complex, there are a number of really, really interesting objects. So if you see just to the right of center, there's sort of this weird sort of peak shape. It almost looks like a nose, almost like a face looking sideways. Now, if you can share to my screen, Mark? That'd be great.
Oh.
I've got an image close up in this region. So that peak is this region here. It doesn't
I've seen
have
this before.
Yeah, it doesn't have a common name. The only the only index number that I could find for it was BBW56, Bock, Bester, and Wade 56. So it's this really sort of rarely imaged target, but I think it's fantastically beautiful. It to me it looks like a mountain, right? This giant, gassy, ghostly mountain, and this is a really sort of iconic example of something called a cometary globule. And it's named a cometary globule because it sort of looks like a comet, right? You can almost see at the peak of the mountain is where the nucleus of the comet would be, and this sort of V-shaped tail flowing out from behind it. And it almost does look like a mountain, right? But obviously in space, mountains aren't formed like they are here on Earth with tectonic activity. Now, this mountain is actually formed from the fast stellar winds from this ancient supernova that happened. And it's sort of blowing it from both directions into this really great sort of mountain peak-like shape. And if we were to look at the full image of the Gum supernova remnant, as we were talking about, there's also this embedded Vela supernova remnant, this sort of bluish region you see here. And I've also taken an image right deep down in this section here. I'll show that to you here. So this is a part of the Vela supernova remnant. So another remnant of a supernova, so a star that exploded in an extremely violent death, some thousands of years ago. And the shock wave from that explosion is slowly propagating out through space, collecting and exciting some of the gas that's out there on that way. I think this is one of my favorite images. This took me nearly 16 hours of integration time from the dark sky site. But I think it's just amazing to see the sort of detail in all of the filaments, all of these sort of shock waves that have been propagating. And so this is a hydrogen alpha and oxygen 3 image. The hydrogen alpha mapped to the red and the oxygen 3 mapped to the blue. But yeah, really, it's sort of a more challenging target to image. It's very dim, and it sort of requires you to use these specialized narrowband filters. But when you get a bit more experience in astro imaging, this whole Vela supernova remnant, Gum supernova remnant is an absolute playground. So absolutely, I recommend people, give it a go. It's really absolutely beautiful. And yeah, I'll leave it to Claire to talk about some of the details of this.
Have you got anything to add, Claire?
I've got plenty. Come on.
Go for it.
Okay, so I'm just going to say that, so there's about 32 of these cometary nebulae that, like you said, Stefan, and absolutely beautiful images. Oh, my goodness. And as you said, they're called cometary nebulae. They're just like Bock nebulae, except they're shaped in this kind of like blowout sort of comet sort of thing. And what's really cool is, as you're quite right, that sort of cloud there that is around the Vela supernova remnant is the stuff that originally formed the star that blew up. So these cometary nebulae are the clouds that formed the star that then basically grew up to bite the hand that feeds them. So what these are called type 2 supernovae, and they're the ones that basically big stars, so between 4 and 8 times the sun's mass, possibly more, they explode in this shockwave when they run out of fuel, basically, and they can't hold their outer layers out anymore, and gravity collapses it down, and the energy hits the core, and it's this big shockwave. And if there's enough material left over at the end in the center, or it can come together enough, it's got to be between 1.4 times the mass of the sun and about 3 times the mass of the sun, because any more than 3 times the mass of the sun that's left over, it becomes a black hole. And any less than 1.4 times the mass of the sun, basically the electrons are able to resist each other and the protons and not go any further with the collapse. So we get what's called a white dwarf, which is what the sun will be. So less than 1.4, you get white dwarfs. which is smaller masses, more than about 3, a little bit more maybe, depending on the conditions, you get a black hole. And so in between, you get these things called neutron stars. And what they are is, this, if you want to basically think about it, it's essentially all the electrons and all the the protons that are left in the middle get forced into each other. So you've got a negative and a positive get forced together, and they make neutral particles or neutrons. And so the entire mass inside just becomes extremely dense, like 10 kilometers across, and they're fully made of neutrons. And this is what we call a neutron star. And because they're so massive, they've got heaps of gravity, and they've got lots and lots of sort of, we think, magnetic fields associated with that. And they usually are spinning really fast. If you think about sitting on a chair with your arms out and then you bring your arms in, that's basically what happens. The star's got rotation, of course, because rotation is actually easier than sitting still. There are many forms of movement and only one form of stationary. So it's likely the star had some rotation, and then when it collapses this tiny little thing, it's spinning really fast. So it actually spins this neutron star spins over 11 times every second. And we know that it's spinning because it's a type of neutron star called a pulsar, which is essentially the magnetic fields that are associated with this gravity. They form these big jets of material, and the jets just happen to be aligned with Earth. So the jet sweeps across Earth, a bit like a lighthouse over a boat. So a lighthouse beam over a boat, and they sweep around Earth every time this pulsar spins. And these are like 11 times or more every second, and they can be spun up by actually accreting more material. But what's kind of cool is the velar pulsar, which is the brightest one that we know, actually has these things called glitches, right? And the timing, which is usually super regular, right? So you can actually time things by pulsars. This particular type of pulsar has these things called glitches, which is still pretty much not really understood. There's a whole lot of work going on at the University of Melbourne under Andrew Milados, who was looking at basically the compact surface of neutron star just gets the most tiny little mountain, like we're talking like mils, and that's what causes these glitches when they collapse. So they're really not understood, and the velar pulsar, despite the fact that it happened, 11,000 years ago, is still so fascinating because of what it represents.
I'm trying to catch my breath after that one.
Sorry, I got very excited.
No, that is gold. I'm. Here we go. Velar pulsar. Sorry, I'm just trying to catch up. Lee's in space engine at the moment, and he's moving to the Velar. This is what I love about astronomy, when people are so passionate. Like Stefan was running on with his stuff, and then you're running on with your stuff, and most of this stuff goes over my head. I will admit to that. But it's all just so enjoyable and exciting to hear it, you guys speak about it, and for our viewers to watch and learn. Now, while this is happening, Kim, we have Gully Winds.
Yep.
Might be able to help you out with the memorial with my contacts. So gullywinds@hotmail.com.
Yeah, I've made a note of that
email.
I can't reply directly now, but I will.
I'll later on, if you can send an email to Gully Winds, I believe they can help you out with that memorial for with regards to Gum Nebula. That'd be amazing. Now,
Space Engine actually goes to the Velar pulsar, but it doesn't show anything. So this is just another random one, GS2023-338A, just showing the jets of the pulsar as Claire described it. So we end up seeing that sort of motion, I think, in...
Is that right, Claire? Is that what we see?
Well, it can be in any orientation. So a pulsar could be spinning completely with its axis, completely, I suppose, 90 degrees, or the axis would be aligned with our sight. So we would see both jets go blip, blip, blip really regularly, or we might see, if it's slightly angled, you might see the top go round, and pass over. We might have it sort of spiraling. When they're blazing straight at us, they're Yeah, that flash is very, very regular. But, they could be slightly oriented, a little bit, I guess, off center. But usually the ones we see are the ones that are in line with the jets, with our line of sight.
Do we see some that will spin like a lighthouse as well, similar to this, even though this one here isn't spinning, obviously?
They have to be spinning. That's what gives it the pulse, yeah.
You're making stuff up now, Lee.
Yeah. Oh,
are you able to, Lee, while you've got this going, can you go to Shapley 1 for me? Because we did have Paul on, and Paul had an image that he'd taken of Shapley 1, or Shapley 1. And I've imaged Shapley 1 with my phone using the ASV's 40-inch telescope. And I blew my mind that I could do that with a phone. I still don't believe that it happened, but I did. It is a planetary nebula. So, Stefan, Claire, get your skates on with this one. It's an amazing object. It's quite impressive to see live through a telescope, I will say that. I know that the ASV's Deep Sky Section Director is a big fan of it as well. The space engine's not going to do justice to it that Paul Hayes's image did. That's for sure. And I think we've just lost Andy from a stream, so that he will come back, no doubt. So this is a planetary nebula. One of those confusing ones, and Andy's back. We'll just add him into the stream quickly and go back to the live view. So, Stefan, do you want to talk a little bit about Shapley 1?
Sure.
Planetary nebulas.
Yeah, like you said, it's a planetary nebula, which is a really confusing name to anyone who's not looked into astronomy before, because you think, wait, is it a planet? Does it have something to do with planets? No, it doesn't. But when we first observed planetary nebula, we thought that's what they were. It had some association with planets because they're small, they're bright, and old astronomers used to think, oh, maybe they're planets, but they don't really move. There's a lot of confusion. But now we know that planetary nebulae are actually like the final form of stellar mass black holes. Stellar mass stars, sorry. So stars much larger than our own sun, we know that when they end their life, they will probably turn into neutron stars, like we were talking about with the Valon pulsar, or they'll turn into black holes. But if they don't have enough mass, then they'll shrug and they'll release some of their outer layers into this sort of halo of gas, but their core won't crunch down into a neutron star or a black hole. It'll remain as a white dwarf. And this is going to be the eventual fate of our own sun. Our sun isn't massive enough that it'll turn into a neutron star or a black hole. It will turn into a planetary nebula. Eventually, our sun will swell up into a red giant, and then those outer layers will just sort of dissipate out into space. And that's exactly what's happened here with this planetary nebula. Now, Shapley 1 is a little bit special. Usually, we expect planetary nebulae to sort of release their outer layers uniformly in a sort of spherical structure. But this is a type of planetary nebulae called an annular planetary nebula, or a toroidal planetary nebula. Torus meaning a sort of donut-shaped object. So if we zoom around to around perpendicular to this object, you'll see that it's sort of got this donut, sort of tire-looking shape. And we're just seeing it from Earth face on. So we see it like this perfect ring almost. Now, this planetary nebula is around 4,900 light years away in the constellation Norma, and its magnitude 12.6. So it's very, very dim. So you'll need a big telescope or a fast telescope to be able to image or see this. And it, like most planetary nebulae, appear fairly small in the sky. It's only around 1 arc minute in diameter, as we see from Earth, which is about as big as a large crater on the moon. So relatively small. But yeah, this particular planetary nebulae started forming around 8,700 years ago, when it started shedding its outer layers, which we're sort of seeing now.
Yeah. Lee, can I get you to just scroll that back just a touch? No, back. Yep, back a bit more till it just is. Yep, about there. Now that is about the size, maybe a little bit smaller, as what you will see through the ASV's 40-inch. And we've got a comment here, Tamara Gamil. And Tamara, hello. I remember you coming up for Deep Sky, yes. And we did look at this through the 25-inch a couple of weeks back before lockdown. And this is kind of, I mean, it's a little bit better than what it looked like. But this is about what it looked like from a visual point of view. It was a little bit, bit duller. That's about it there. Bit too dull there, Lee. But yes, we did visually see this object through the ASV's 25-inch telescope. It looks amazing through our 40-inch telescope as well. You can visually see this from our dark sky site, that's for sure. Now, we have an image that Paul Hayes, and Paul, if you remember, had a hailstorm and lost power. But Kim has his image ready for us to look at.
Yeah, so this is
the details on this image.
Yeah, it was about 21 hours of hydromet.
Is that all? Just a day's worth of...
through a 12-inch f4 scope. But you can see the multiple layers here quite nicely in this image. So, yeah, that's the image that Paul had of it. He has another one on his website, but that's the one I've selected for now. But yeah, it's quite an impressive image. I'd really like to see that through a scope.
It's absolutely amazing to look at through a telescope. That I can say. I've seen it through the 25-inch. I've seen it through the 40-inch at our dark sky site, and it's an absolute favourite of our deep sky section directors. It's a beautiful object to visually look at. Claire, did you have anything to add to the discussion of Shapley 1? Or Shapley 1, sorry.
I mean, I could just generally add some planetary nebulae discussion. Essentially, what happens in most stars that we see outside, what we call a main sequence star, inside the star is what we call hydrogen fusion. So it's literally what it sounds like. It's nuclei of hydrogen being forced into, so protons being forced into other protons to make helium. And so basically what's forcing that to happen is the immense amount of mass. So we've got gravity pushing the star inwards. We're talking about lots and lots and lots of mass here, like the sun, obviously, pushing down. That's a lot of gravity, right? Pushing in towards the center of the sun, forcing the fusion, the two protons together or whatever. And what happens is that when those things fuse, when the hydrogens fuse, so they need some energy to be pushed together, right? But once they do fuse, they release a lot more energy. And so that's where the shining of the sun comes from. So you've got this constant balance going on between gravity pushing inwards and the light energy and the heat and all that sort of stuff making its way out to the surface, which pushes the layers outwards. And that's actually what we see in stars. So they're sort of in this equilibrium. And that's what we call the main sequence, when it's hydrogen fusing in the core. When hydrogen sort of starts to run out, and it does it in a few layers, but when hydrogen in the core basically starts to run out and we've got mostly helium, what happens is that the star kind of goes, oh, what do I do? Oh, no. And essentially there's not enough energy pushing those outer layers out anymore. And so those outer layers start to come in, right? So they actually contract a little bit before the next phase. And by contracting, we've now got a lot more mass, right, in a much smaller area. And so instead of about 15 million Kelvin, which is what it was originally when it was fusing hydrogen, the temperature suddenly shoots up to about 100 million Kelvin, right, with this density, and helium starts to be forced into other helium. And so we get helium fusion. Now, helium fusion, once those heliums are forced together, they actually produce a lot more energy per fusion event than hydrogen does. So suddenly this star produces heaps and heaps of energy, which then, of course, pushes those outer layers out a long way, way beyond what they were being held out when there was hydrogen fusion going on. And this is what we call the red giant phase. And so now these layers are a long way away from the center, and they're only tenuously held on, right? And every time that helium sort of gets used up a little bit, it sort of puffs out in shells. So as you go out from the radius, it sort of burns in shells. Well, not burns, it fuses in shells. And the star contracts and it releases, and it contracts and it releases, kind of almost like a breathing, right? Between the gravitation pushing in and the fusion pushing, energy pushing it out. And that's what actually produces these puffs of layers. We call these asymptotic giant branch stars. If you ever want to look that up, it's AGB. It's just off the main sequence. So the main sequence is this nice long straight line when we graph. If you want to look up main sequence stars, they're that nice straight line, and then they kind of peter off and they become these puffing red giants in this sort of death throes of an equilibrium between gravity and energy trying to get out.
Oh, I know AGB is something different, but we won't go there.
That's why I said you can look it up, because, you know, sometimes there are things you shouldn't Google according
No, don't Google that one. Don't Google that one. Now, Lindsay wants to know what this is called. This is Shapley 1. It is absolutely stunning to look at through a telescope. So now, for those of you wondering when I'm talking about a 25-inch and a 40-inch, this is what I'm talking about. So the telescope you can see at the front there, that is the ASV's 18-inch telescope. The one at the back that our Deep Sky section director, wearing a very, very sexy pair of shorts there, is controlling. That's Paul, our Deep Sky section director. That's our 40-inch telescope. So the mirror of the 18-inch that you can see at the front, it's an 18-inch mirror. So if that's an 18-inch mirror and the 40-inch is a 40-inch mirror, the mirror is twice the size. So it is it's a very, very large telescope. I think from memory it stands close to 3.5 meters tall, nearly. Something like that anyway. You can see in the background the ladder leaning up against the wall. You need that ladder to look through that telescope when it's at the angle that it's sitting at the moment in that video. It's an amazing piece of kit. It's beautiful to look at on a clear, crisp night at our dark sky site. Now, the last couple of objects we're going to look at, a couple of planets. We're going to jump across to Jupiter. Even though Anne-Marie's like blur, planets, blur. We're still going to jump across to some planets, look at Jupiter, and we'll look at Saturn, and then we'll finish up for the night. So we'll jump across to Andy's image there of Jupiter. We did a stream the other night of Jupiter where we had Ganymede and Callisto. So I think Ganymede was going into eclipse as Callisto was coming out of eclipse. So if you haven't seen that, it's on our YouTube. It's a really cool little video to watch. It's about an hour's long little stream. Had a few technical difficulties, but we managed to get clear skies for the eclipse, and it's quite interesting to watch. But this is Andy's image of Jupiter. Andy, tell us about this image. And I'm sorry, Neil, Deep Sky is not where it's at. All of astronomy is where it's at.
Well, this image of
radio.
This image of Jupiter I took is a video. It's done what they call lucky imaging, and I used this camera here. It's a little it's a proper planetary camera. It's my guide camera, but I've sort of put it on and use it every now and then, and for taking images like this. And it jumps around the screen, and you think you've got this pretty crappy image. I think these were about 3,000 or 4,000 frames, and then you've got free software like Auto Stack It or Registacks. There's two of them, which then go through each of the frames, breaks up the video into and analyzes each frame. And I think I kept about 20% of these, and then did a bit of slight processing. So this is just through my 6-inch Newtonian and planetary camera. Yeah, so it's not too bad image. You can see the bands. You've got one of the moons. I'm not too sure what moons. The other night it was Io and Callisto, but I think there's 4 moons, Ganymede, and the 4th one, I'll be waiting for someone to tell me.
So are you talking about the other night when we did our live stream?
Yeah, that was Callisto.
That was Callisto and Ganymede.
Ganymede, yes.
So Ganymede went into eclipse as Callisto came out of eclipse. It was pretty cool to watch.
Yeah.
It wasn't like you could see these beautiful circles disappearing. They were little hazy blobs because of working through cloud. But it was still amazing. You could see the little hazy blob of Ganymede slowly get fainter and fainter. And then it disappeared. And there was nothing there for about sort of 7 or 8 minutes. And then Callisto just slowly started to appear piece by piece. It was quite impressive to see. This is, I'm pretty sure this is from Space Engine. I don't know if this is an actual, like, I feel like it's moving faster than it should be. But this is from good old Space Engine. You can see Ganymede and Callisto and Io. And there's only 3 there at the moment, but Europa is the other one. Yes. So there you go, Andy. You've had to wait for Facebook to answer your question. So you can see there, you can see 4 lovely bright objects there on the right-hand side, and there are 4 of the moons. Stefan, Claire's yawning. She needs another beer. You guys got anything you'd like to add to this?
Yeah, I just want to say that Jupiter is absolutely one of the most amazing things to look at through even a pair of binoculars or a telescope or anything. For me, when I first bought my first telescope when I was 15, this absolutely blew my mind. I'd never looked at through a telescope before. I had no idea what to expect, and I pointed it towards Jupiter, and I was just blown away. You know, it wasn't the most amazing view, but I could see 3 of those moons, and I was like, wait, aren't I meant to see 4? And as I kept watching throughout the night, I slowly saw the last 4th Galilean moon emerge from behind Jupiter. And it was this amazing feeling that the universe that I'm looking at isn't static. It's always moving, and we're a part of it. It's one of those really amazing things that you can do with astronomy, that you can connect with the universe around you. So I highly suggest anyone, if you've got a pair of binoculars, whatever you've got, look at Jupiter and, look at it over the night, and it'll absolutely blow your mind. And if you can share my screen, Mark, I've got a little animation. So this one here, this is a video that I've taken of Jupiter. Its rotation over just 1 hour. So you can see that it's sort of wobbling back and forth. I'm just playing it forwards and backwards. But this is the actual rotation of Jupiter over just 1 hour. And that's because Jupiter, even though it's much more massive than the Earth, it rotates a lot quicker. One day on Jupiter is only around 10 hours long. And you can actually record this, with fairly affordable equipment. It's really something spectacular. I think I was quite lucky because on the night that I actually recorded this, there was this one special outbreak in one of the north temperate belts on Jupiter, this outbreak here. And I was able to submit some of these photos to a database, which perhaps may have been used in some science. So I think astronomy is a very special type of science because it's one that citizens, amateurs can still contribute to actively and actually give useful data. So yeah, no matter who you are, no matter what equipment you've got, get out there, get viewing. Yeah, you'll be blown away.
Stefan, I can beat that video. It's not mine. Absolutely not my video. But one of the guys who worked with us on Wednesday night with this eclipse setup, Andrew Amiet, who's a very, very impressive planetary photographer, did a GIF of Ganymede entering eclipse and Callisto exiting eclipse. So I'm hoping I can get this to work. Not sure if we can see this. There you go. You can just make it out. So you can see Ganymede there disappearing and then Callisto appearing.
Beautiful.
So we watched this live. He put this live on the screen on Wednesday night for us. And this is the end result of what he did. So the stuff we were watching live, we watched this live in black and white, and we had Noel's color images going. And then after the event, he processed this and sent it through to me on an email. Neil, it's always a competition. You should know that by now. But no, it's not always a competition. But this is just an absolutely stunning example of what we streamed live for our viewers on Wednesday night to see Ganymede disappear and then Callisto appear out of eclipse.
It's not a competition, says the man who declared that dark sky observing, that deep sky is where it's at and that nothing else is important.
I know. Neil is
about these moons. They are incredible. Like, just even these 4 moons, right? You could spend your life just discovering things about one moon around Jupiter or Saturn, or even if you want to spend time on the Earth's moon, although that's been fairly well studied. Callisto is old. It's got no surface activity really at all. It's so heavily cratered. It tells some seriously cool historical stories about a time in the solar system where everything was going everywhere and hitting everything. So that's Callisto. Ganymede is this really weird shape, like it's been like bonged by something else. And it actually has its own magnetic field, an internally generated magnetic field, which is insane. Ganymede, Io, and Europa also have structured layers on their inside. So they're very much like Earth with different layers. Europa is thought to be an icy moon with water ice inside it, and potentially one of the places we want to go and have a look at for astrobiology, for life, because it's sort of in this habitable zone because it's kept warm by subterranean volcanoes, or sub-ocean volcanoes. And then Io is probably my favorite. It's in this amazing tug of war between the immense gravity of Jupiter and the gravities of Ganymede and Europa. And it's just constantly being pulled apart, basically stretched and stretched and stretched. And so it has tides, just like Earth has tides from the moon. Io has tides from Jupiter and the other moons, but this is not normal tides. This is tides of sulfur. So this stretching is basically pulling the crust, and you're getting these tides of solid sulfur surface that can go up to about 100 meters. And it's basically got volcanic activity. They've got these spurting out sulfur volcanoes. Io is absolutely fascinating. And just covered in all these different compounds of sulfur. So Neil, I challenge you. I actually think there's plenty in the solar system. So there's a competition for you.
He's backing down now. He's backing down already.
I know you're serious.
No, Neil's a good man. Neil's a good man. He's teasing me is what he's doing. So this is what are we looking at, Lee?
That's IO.
IO. There we go. What do I owe you, a beer?
A better joke.
A better joke? I know. I know. It's a dad joke. What can I say? So what we're going to do is we're going to jump, once Lee's finished showing us a fly-through of Io from Space Engine, we're going to jump to Saturn and have a quick chat about Saturn. Unfortunately, it's not clear enough anywhere in the country, really. Well, anywhere we've got telescopes anyway, to live image Saturn. So we're going to go to some images while Lee moves across to Saturn. We're going to have a look at an actual image of Saturn with some of its moons that Stefan has. I'm assuming, Stefan, you've taken this image.
Yes. Yeah.
Yes. Now, tell us. Whoa,
Sorry.
we went a loop at the Matrix there for a while. Tell us a little bit about Saturn, will you? And Anne-Marie, I know you've taken a Saturn image, and I know you're not keen on it, but it's actually pretty good. So get yours ready, please. So, Stefan, floor is yours.
Yeah. So, I mean, what can you say about Saturn, right? It's the most beautiful planet, hands down. I mean, Jupiter's my favorite planet just because of how dynamic it is and how much it changes. But Saturn, everyone has to admit, is the most beautiful planet in our solar system. It's the only one with this obviously visible ring, even though some of the other gas giants do have rings. They're just not quite as visible. But yeah, Saturn has this fantastic ring with this very obvious division, this black division in the middle of the ring called the Cassini division. And in some more high-resolution images, you can see further divisions like the Inky division and some others. And Saturn also has, a large number of moons. There's over 82 moons that have designated names. And in this image, you can see 4 of them. So from top to bottom, there is Dione, then Enceladus, then Tethys, and then Rhea. I'm not sure how many of the moons have names, but yeah, quite a few of the more large ones do. And Saturn, it's a gas giant, so it's not like Mercury, Venus, Earth, or Mars, which have rocky surfaces. It's a gas giant. It's made of gas. It has no solid surface. And actually, Saturn, there's quite an interesting fact about it. Because it's gaseous, its mean density is less than the density of water. So if you had a body of water large enough and plot Saturn on top of it, Saturn would actually float on top of that water. So, yeah. Does anyone have anything else they'd like to say?
Claire, would you like to add to that?
Yeah, I love the second one you said, Enceladus, which I always think sounds like salad, like the salad moon. But Enceladus is actually really...
Is that for the healthy astronomers?
Well, I don't know, the healthy people that need something to remind themselves of all these random names. So Enceladus, Cassini flew past Enceladus in 2015, and before then, we thought, Enceladus is just basically, it's just an icy sort of moon. But when Cassini went past, it actually detected a magnetic field, or it detected something that was pushing on the magnetic field of Saturn, right? And so when they actually did a targeted flyby, Cassini went through and had a look, and Enceladus is actually an active moon. So they think that it has some salty liquid underneath its icy surface, and it actually has these geysers of salty ocean brew, right? And of course, if you know some chemistry, salts can sort of carry electrical current, and that's kind of where the association with the magnetic field comes from. And so you get these organic chemicals and these salts and this sort of brew coming out of these geyser volcanoes on the surface of Enceladus. It's absolutely fascinating. But what's really cool, if you don't just want to look at the sky, there's actually the magnetometer readings have recorded what they call ion cyclotrons. So essentially there's these packets of material flowing between Enceladus and Saturn, of ionized pieces of material flowing on these sort of magnetosphere lines, these lines, magnetic lines between the moon and the planet. And that's been recorded. And you can actually listen to a sonification or a conversion of the data to sound, and it is the weirdest thing you'll ever hear. So if you feel like it, feeling creeped out after this, you can go and actually Google NASA or ESA, Enceladus, sound of Enceladus, or sound of magnetic field on Enceladus, and it is just an awfully creepy sound. I'd play it for you, but I'm having trouble sharing things.
That challenge accepted. I think go and have a listen to that. I think I've actually heard that before. I'm sure I have, yeah. So that actually brings us to the end of our live stream. There's only 7 of us left. We lost Perth. They disappeared. Paul had a blackout, which is fair enough. but there are 7 of us left standing, and we thank you all for coming along tonight to listen to us shoot the breeze on astronomy, and we hope we sort of gave you a little bit of a break from lockdown life in Australia at the moment, and hoping it ends soon. If it doesn't, and I know for Sydney it won't, Melbourne I'm not so sure, Adelaide I think you guys will be right, but if it doesn't, we will definitely, some of us will definitely be back next weekend to do another stream, and hopefully we've got some clear skies and we can do some actual live stacking, because that would be pretty cool. It's been a while since we've been able to do that, and we're kind of all missing that, to show you live images as they appear, that's for sure. We do have Lee has put together a lovely little somber montage for us to leave you with, so I will play our lovely outro, and we will leave you with it. And thank you to everybody who came along to help me out tonight on this live stream, and to everyone who tuned in to view. And hopefully we don't have to see you next weekend, but if we do, we will enjoy sharing the night sky with you.
Hello, darkness, my old friend. I've come to talk with you again, 'cause a vision softly creeping lifted seeds while I was sleeping, and the vision that was planted in my brain still remains within the sound of silence. Restless dreams I walked along narrow streets of cobblestone, neath the halo of a street lamp. I turned my collar to the cold and damp. When my eyes were stabbed by the flash of a neon light, it split the night and touched the sound of silence.